in a remote galaxy billions of light years away. A star 100 times more massive than our sun is dying. For a brief moment, it will unleash more energy than 1,000,000,000,000 suns combined, sending shockwaves across space-time itself. The light from that explosion, a messenger carrying tales of cosmic violence, began its journey when Earth was still a molten world, a formless sphere of rock and fire. That light is now arriving, painting our telescopes with the final, brilliant act of a stellar giant. We perceive it as an event happening tonight. Yet the star itself has been a black hole or a scattered cloud of dust for eons. This delay, this gap between an event and its observation, is not a mere inconvenience. It is a fundamental law of the cosmos, a barrier that separates what is from what we can know. The universe is not a static picture we view through a window. It is a story told in echoes, and the narrator is light, a traveler bound by an absolute speed limit. That limit, 186,000 miles per second, is both our connection to the cosmos and our ultimate prison. It means the farther we look into space, the deeper we look into time. Seeing galaxies as they were when the universe was younger, smaller, and more turbulent. The starlight that reaches us from the Andromeda galaxy, our nearest major neighbor, departed 2.5 million years ago. Beings on a planet in that galaxy, looking toward the Milky Way, would not see our civilization, our cities, or our satellites. They would see a sky where Earth is inhabited by early hominids, still millions of years away from forging tools or questioning the stars. Our present remains invisible to them, just as their present is a secret kept from us, locked behind a 2.5 million year wall of time. This cosmic horizon, the edge of what we can possibly see, is not a physical wall but a boundary of information. Beyond it lies a universe we can theorize about but never directly observe. Light from those unimaginably distant regions has not had enough time to reach us since the beginning of everything. 13.8 billion years ago, the universe might be infinite, stretching on forever with countless other galaxies, stars, and perhaps even other forms of life. But our knowledge is confined to a finite bubble, a sphere of observation with Earth at its center. Every direction we look, we see the past, and at the ultimate edge of that vision lies the faint, lingering glow of the universe's birth. This wall of light, the cosmic microwave background, is the oldest photograph we will ever possess. A baby picture of the cosmos when it was just 380,000 years old. It is a relic of a time when the universe was a hot, dense fog. Before the first stars ignited, before the first galaxies coalesced. It is the echo of creation, a whisper that fills all of space, carrying the seeds of everything that would ever exist. This boundary defines our reality, a testament to the fact that we are participants in a cosmic story that began long before we arrived and will continue long after we are gone. We are latecomers to a drama of unimaginable scale, piecing together its plot from the ancient light that falls upon our world. Deep inside every atom in your body, an invisible war is raging. Protons packed together in the nucleus should tear themselves apart instantly. Their positive charges repel each other with tremendous force, like trying to push two powerful magnets together. Yet somehow they remain locked in place by the strongest force in the universe. The strong nuclear force operates at distances smaller than a single proton, but its power is absolute. Scientists measure it as 100 times stronger than electromagnetism and 100 trillion times stronger than gravity. If gravity were a whisper, the strong force would be a thunderclap, that could shatter mountains. This force, the silent guardian of matter, is what allows existence as we know it. Without it, the universe would be a thin, uniform soup of hydrogen, a sea of lonely protons and electrons with no complexity, no stars, no planets, and no life. It is the architect of structure, the power that forges the elements in the hearts of stars and holds them together against the immense pressure and heat. Its very nature is a paradox of scale, a force of unimaginable might that operates only across the most infinitesimal distances. It is the titan in the atom, the power that builds worlds, one nucleus at a time. This force works through particles called gluons, which act like invisible chains, binding quarks together to form protons and neutrons. The more you try to pull these fundamental particles apart, the stronger the force becomes. It is like stretching a rubber band that grows thicker and more resistant with every inch you pull. This bizarre behavior, called confinement, means you can never isolate a single quark, no matter how much energy you apply. When you try to separate quarks, the energy you add simply creates new quarks and gluons, like trying to cut a chain only to have it grow new links. Inside each proton, 3 quarks dance in a prison of pure energy, a web of interactions so complex that even our most powerful supercomputers struggle to model it. This quantum prison is the foundation of all matter. It ensures that the building blocks of the universe remain stable, that protons do not decay into a spray of more fundamental particles, that the very substance of our reality holds together. This force shapes the very building blocks of matter. It determines which atomic nuclei can exist and which cannot. It sets the rate at which stars burn their nuclear fuel, a cosmic thermostat that dictates the lifetimes of suns. It controls the balance between creation and destruction in the hearts of every star across the cosmic void. Yet despite its incredible power, the strong force has a fatal weakness. Its reach extends only to the edge of an atomic nucleus, about 1/10,000,000th the width of a human hair. Beyond that microscopic realm, its influence vanishes completely, and other powers take control. It is a giant confined to a subatomic cage, a king whose absolute authority ends at the palace gates. Our spacecraft engines ignite with the power of 1,000 suns as we break free from Earth's gravitational embrace. The blue marble that has been humanity's home for millions of years shrinks to a pale dot behind us, then disappears entirely into the cosmic darkness. We are now truly alone in the void, beginning the longest journey any conscious being has ever attempted. The first challenge hits us immediately: the sheer scale of what we are attempting. To reach Andromeda, we must travel a distance so vast that light itself, moving at 186,000 miles per second, takes 2.5 million years to make this journey. If we could drive there in a car at highway speeds, never stopping, never sleeping, it would take us 30 billion years. But we have technology beyond current human imagination. Our vessel bends space and time around itself, creating a bubble of warped reality that allows us to slip between the normal rules of physics. We accelerate not through space, but through the fabric of space-time itself. The stars around us begin to shift and blur as we approach speeds that would have been impossible just moments before. This is the only way to traverse the void, not by conquering distance, but by redefining it. By treating the universe not as a space to be crossed, but as a tapestry to be folded. The journey is not just a physical one, it is a conceptual one, a shift in understanding how reality itself is constructed. As we leave our solar system behind, we pass through the Kuiper Belt, where ancient chunks of ice and rock drift in eternal darkness. These are the leftover building blocks of our solar system, frozen in time for 4.5 billion years. Pluto, once considered our 9th planet, appears as a lonely sentinel guarding the edge of everything we have ever known. It is a world of nitrogen glaciers and mountains of water ice, a testament to the cold, slow processes that shape the outer reaches of a star's influence. Beyond Pluto lies the Oort cloud, a spherical shell of icy objects that extends nearly a light year from our sun. This is where comets are born, in the frigid depths where temperatures drop to just a few degrees above absolute zero. We are entering a region where the sun's influence barely reaches, where the space between objects is so vast that collision is nearly impossible. The nearest star to our sun, Proxima Centauri, glows like a red ember in the distance. It would take conventional spacecraft over 70,000 years to reach it. But we pass it in what feels like minutes. We are now in interstellar space, the vast emptiness between star systems, where matter is so sparse that you could travel for millions of miles without encountering a single atom. This is where most space travelers would feel the crushing weight of isolation. But we push forward with purpose. The Andromeda Galaxy beckons from across the cosmic ocean, its spiral arms slowly rotating in a dance that has continued for billions of years. We are no longer bound by the limitations of our species or our world. We are explorers of the infinite. The very concept of a journey on this scale forces a re-evaluation of time. The 2.5 million years it takes light to cross the gulf between our galaxies is a period longer than the existence of our own species. Civilizations could rise and fall in the time it takes for a single photon to complete its voyage. The universe operates on timescales that make human history seem like the briefest flicker of a candle in a storm. Our technology, which folds space-time to make this journey possible, does not conquer time itself. It merely creates a pocket of local time, a bubble of distorted physics where our clocks tick at a different rate from the universe outside. For us, the journey may take years, but for the cosmos, millions of years will have passed. We will arrive in a future we can only guess at, a galaxy that has aged and evolved in ways we cannot predict. This temporal dislocation is the true price of cosmic travel. We are not just explorers of space. We are time travelers, adrift in the currents of a river that flows at different speeds in different places. The loneliness of the void is not just about the absence of matter. It is about the separation from a shared moment, a disconnection from the universal clock that governs all things. We are becoming untethered from our own history, an island of consciousness moving through a sea of time. This journey through the void is also a journey through the unseen. We enter the local void, a region of space so empty it defies comprehension. Here, between the galaxy clusters, matter exists in concentrations so low that an entire cubic meter of space might contain only a single atom. The temperature drops to just a few degrees above absolute zero, and the only light comes from distant galaxies billions of light years away. This is cosmic loneliness on a scale that breaks human understanding. If Earth were placed in the center of this void, our night sky would be completely black except for the faint glow of the Milky Way itself. No other galaxies would be visible to the naked eye. Ancient civilizations would have developed entirely different mythologies, religions, and scientific theories about the universe based on this profound isolation. But the void is not truly empty. Dark matter, the mysterious substance that makes up 85% of all matter in the universe, forms invisible scaffolding throughout this region. We cannot see it directly, but its gravitational influence shapes the very fabric of space-time around us. Our instruments detect its presence through subtle variations in the cosmic microwave background radiation, the afterglow of the Big Bang itself. It is the ghost in the machine, the silent architect of cosmic structure, holding galaxies together and guiding their dance across billions of years. As we travel deeper into the void, we encounter something unexpected: rogue planets, ejected from their home solar systems by gravitational interactions with passing stars. These orphaned worlds drift through the darkness, no longer warmed by any sun, their surfaces frozen solid, and their atmospheres collapsed into ice. One rogue planet we encounter tells a particularly haunting story. Its surface shows evidence of ancient oceans kilometers thick. Beneath that ice, our scanners detect something remarkable: a subsurface ocean, kept liquid by the planet's own radioactive decay. In this hidden sea, completely isolated from any star's light, primitive life forms might still exist. Evolved from organisms that survived their world's ejection into space billions of years ago. Life, it seems, can find a way even in the most desolate corners of the universe, a testament to its tenacity and adaptability. The void also contains the remnants of ancient galaxy collisions. Tidal streams of stars, stretched across millions of light years, mark the paths where smaller galaxies were torn apart by the gravity of larger ones. These stellar graveyards tell the violent history of cosmic evolution, where galaxy clusters grow by cannibalizing their smaller neighbors in a process that continues to this day. We pass through regions where the cosmic web itself is visible: vast filaments of dark matter and ordinary matter that connect galaxy clusters across hundreds of millions of light years. These structures formed in the early universe, when matter first began to clump together under the influence of gravity. They are the highways along which galaxies travel, the channels through which matter flows from one region of the universe to another. The silence here is absolute, broken only by the faint whisper of cosmic rays, high-energy particles traveling at nearly the speed of light, accelerated by unknown processes in the violent hearts of distant galaxies. These particles are messengers from the most extreme environments in the cosmos, carrying tales of stellar explosions and black hole jets. They are a constant reminder that even in the quietest parts of the universe, the echoes of unimaginable power can still be heard. Our journey is not just a passage through empty space. It is a reading of a cosmic history written in the language of gravity, light, and a silence more profound than any sound. Somewhere in the cosmos, a beam of pure energy tears through space at nearly the speed of light. For just 10 seconds, it releases more power than our sun will produce in its entire 10 billion-year lifetime. This is a gamma ray burst, and it represents the most powerful explosion the universe can create. These cosmic titans occur when the most massive stars in existence, stellar giants containing the mass of 20 to 100 suns, collapse into black holes. When these monsters finally exhaust their fusion reactions, gravity wins the ultimate battle. As the star's core implodes, it fires jets of matter and energy from its poles at 99% the speed of light. The collapsing core creates a newborn black hole surrounded by a disk of superheated material. Magnetic fields, twisted and amplified by the collapse, act like cosmic cannons, launching these jets outward with impossible precision. The jets punch through the dying star like bullets through tissue paper, emerging as focused beams of destruction that remain tightly collimated across vast distances. A single gamma ray burst can outshine 1 trillion stars. If you could see gamma rays with your eyes, These explosions would appear brighter than the full moon, even from galaxies billions of light years away. The energy released in seconds exceeds what 10 trillion hydrogen bombs could produce if they exploded every second for the entire age of the universe. The most powerful gamma ray burst ever detected, nicknamed the Boat for brightest of all time, occurred in October 2022. It was so intense that it saturated gamma ray detectors across the solar system and created detectable changes in Earth's upper atmosphere from a distance of 2 billion light years. That gives you a sense of how impossibly powerful these events truly are. The light we detect traveled for billions of years, carrying news of stellar deaths from when the universe was young and stars were more massive and violent than anything we see today. Scientists have detected bursts so distant, their light began traveling when the first stars were being born, less than 1 billion years after the Big Bang. These ancient beacons give us glimpses of the early cosmos, when massive stars lived fast and died violently, seeding space with heavy elements essential for later generations of stars and planets. But compared to what lurks in the darkness between galaxies, even these titans pale in comparison. At the heart of our galaxy sits a monster 4 million times more massive than the Sun. Sagittarius A star devours everything that ventures too close, from gas clouds to entire star systems. Yet this giant is considered small compared to the true titans of the cosmic deep. Some supermassive black holes contain the mass of 40 billion suns, compressed into a region smaller than our solar system. They are like cosmic vacuum cleaners, with gravity so intense that nothing, not even light, can escape once it crosses their event horizon. Space and time bend around them like water swirling down a drain, creating distortions that would seem impossible if we did not observe them directly. These gravitational monsters did not grow slowly. The most distant quasars shone from when the universe was less than 1 billion years old, powered by black holes that somehow grew to billions of solar masses in the cosmic equivalent of a few minutes. Normal stellar evolution simply cannot explain their existence. The leading theory suggests these giants began as massive seeds formed directly from collapsing gas clouds in the early universe, containing hundreds of thousands of solar masses from the moment of their birth. When gas spirals into a supermassive black hole, friction heats it to temperatures of millions of degrees. The material forms an accretion disk that glows brighter than 100 billion stars. The disk rotates so rapidly that matter near the inner edge travels at significant fractions of light speed, experiencing time dilation effects that would stretch seconds into hours for outside observers. The most luminous quasars can be seen from across the observable universe, like cosmic lighthouses broadcasting their presence across billions of light years. They outshine their entire host galaxies, making the combined light of hundreds of billions of stars seem dim by comparison. The most violent black holes launch jets of particles at nearly light speed, creating beams that stretch for hundreds of thousands of light years. These jets carry enough energy to reshape entire galaxies, heating gas clouds to millions of degrees and preventing new stars from forming across vast regions of space. The jets can remain active for millions of years, continuously pumping energy into their surroundings. Recent observations have revealed black holes that seem too massive for their host galaxies, breaking the normal relationships between central black hole mass and galactic properties. These overmassive giants challenge our understanding of how galaxies and their central black holes evolved together. They suggest a more violent, chaotic past, where mergers and cosmic collisions played an even greater role in shaping the universe than we previously thought. Something magnificent appears in the distance as we navigate the intergalactic medium. A galaxy cluster containing hundreds of individual galaxies, each one an island universe in its own right. The Virgo cluster spans 13 million light-years across space, containing more than 300 galaxies bound together by gravity in a cosmic dance that has continued for billions of years. As we approach this stellar metropolis, the scale becomes overwhelming. Each galaxy contains hundreds of billions of stars, and many of these galaxies are larger than our own Milky Way. Some are elegant spirals with arms that sweep through space like frozen fireworks. Others are massive ellipticals that glow with the combined light of 1 trillion ancient suns. The largest galaxy in the cluster, Messier 87, dominates the central region like a cosmic giant. This massive elliptical galaxy contains over 1 trillion stars and harbors one of the most powerful black holes ever discovered. The black hole at its center is so massive that it contains the equivalent of 6.5 billion suns, and it is actively feeding on surrounding matter, creating jets of plasma that shoot out from its poles at nearly the speed of light. These jets extend for thousands of light years, creating a cosmic lighthouse that can be seen from billions of light years away. The energy released by matter falling into this black hole is so enormous that it heats the surrounding gas to millions of degrees, creating a hot, glowing atmosphere that pervades the entire galaxy cluster. Between the galaxies, we discover an invisible ocean of superheated gas, heated to temperatures of 50 million degrees Celsius by the gravitational energy of the cluster itself. This intergalactic medium contains more matter than all the stars in all the galaxies combined. Yet, it is so diffuse that it is completely invisible to the naked eye. Only our most sensitive instruments can detect its presence through the X-rays it emits as it radiates away its enormous heat. The cluster is also filled with dark matter, which makes up about 85% of all the matter here. This mysterious substance forms an invisible scaffolding that holds the entire cluster together, preventing the galaxies from flying apart despite their enormous speeds. Some galaxies are moving through the cluster at over 1,000 kilometers per second, fast enough to travel from Earth to the Moon in just 6 minutes. As we navigate through this cosmic city, we witness ongoing galactic interactions. Smaller galaxies are being torn apart by tidal forces, their stars stripped away to form long streamers that will eventually be absorbed by larger galaxies. This is galactic cannibalism on a massive scale, where the strong devour the weak in a process that has shaped the evolution of galaxies since the early universe. We witness something extraordinary: 2 galaxies locked in a gravitational death spiral, their collision unfolding over hundreds of millions of years. The antennae galaxies, once separate and distinct, are now merging in a cosmic catastrophe that will reshape both systems completely. Their spiral arms have been stretched and distorted into long tidal tails that extend for hundreds of thousands of light years. Resembling the antennae of a cosmic insect, the collision zone is a stellar nursery of unprecedented violence. Gas clouds from both galaxies are smashing together at speeds of hundreds of kilometers per second, compressing and heating the interstellar medium until it reaches temperatures where new stars can form. The rate of star formation here is 10 times higher than in normal galaxies, creating brilliant clusters of young, hot stars that burn with the intensity of blue-white diamonds. The merger is also creating something entirely new: globular clusters, dense balls of stars that will survive long after the collision is complete. These stellar cities contain hundreds of thousands of stars packed into regions just a few dozen light years across. They are among the oldest objects in the universe, and new ones are being born in the chaos of this galactic collision. As we watch this cosmic catastrophe unfold, we realize we are seeing the future of our own galaxy. In approximately 4 billion years, the Milky Way will collide with the Andromeda galaxy in a similar cosmic dance. The collision will take place over hundreds of millions of years, gradually reshaping both galaxies into something entirely new. The space between the colliding galaxies is not empty. It is filled with streams of stars that have been torn from their home galaxies by tidal forces. These stellar refugees will wander through intergalactic space for billions of years, no longer bound to any particular galaxy, despite the apparent violence of the collision. Individual stars rarely collide with each other. The distances between stars are so vast that most will simply be redistributed into new orbits around the merged galaxy's center. However, many planetary systems will be disrupted, their planets flung into new orbits or ejected from their home systems entirely. The collision is also creating something beautiful: shock waves that compress the interstellar medium and cause it to glow with brilliant colors. These cosmic fireworks paint the merger zone in shades of red, blue, and green, creating one of the most spectacular sights in the universe. This is the creative power of destruction, a force that tears down old structures to build new ones, a cycle of death and rebirth played out on a galactic scale. The universe is not a quiet, static place. It is a dynamic, evolving system, shaped by the constant interplay of gravity, matter, and energy. And in its most violent moments, it reveals its true, creative potential. But even these titans bow to forces that operate on scales beyond imagination. Across 13.8 billion light-years of space, an invisible force is winning a cosmic war. Every second, it pushes galaxies farther apart, stretching the very fabric of space-time itself. This mysterious power, called dark energy, makes up 70% of everything that exists. Yet, we know almost nothing about what it actually is. Dark energy is not like other forces. It does not weaken with distance like gravity or electromagnetism. Instead, as space expands, more dark energy appears to fill the void. The bigger the universe becomes, the faster it expands. It is like a cosmic gas pedal that only knows how to accelerate, growing stronger as it pushes everything apart. Scientists discovered this force by accident while studying distant supernovae in the 1990s. They expected the universe's expansion to be slowing down due to the gravitational pull of all the matter within it. Instead, they found the opposite. Space is expanding faster today than it was billions of years ago, as if some invisible hand is pulling everything apart with increasing strength. Think of the universe as a balloon being inflated by an invisible breath. Dark energy is that breath, causing every point on the balloon's surface to move away from every other point. Galaxies ride this expanding space like boats on a swelling ocean, powerless to resist the tide that carries them into the cosmic deep. The amount of dark energy in the universe increases as space expands. This seems to violate the conservation of energy, one of the most fundamental laws of physics. Yet, observations consistently show that the energy density of dark energy remains constant even as the volume of space grows. Where this extra energy comes from remains completely unknown. It is as if the universe is creating energy out of nothing, a constant, pervasive miracle that defies our most basic understanding of reality. Current theories suggest dark energy might be a property of space itself, a kind of cosmic constant that Albert Einstein originally proposed and later called his greatest blunder. He introduced it to create a static universe, but perhaps he was right for the wrong reason. It may be the intrinsic energy of the vacuum, a baseline energy level that permeates all of reality. Others think it could be a dynamic field, a form of energy called quintessence that changes over time, or even evidence that our understanding of gravity needs major revision on cosmic scales. Whatever its true nature, Dark energy is the dominant force in the universe's evolution, the silent driver of its ultimate fate. It is a force that does not act on objects, but on space itself. A constant, irresistible pressure that is slowly, inexorably, pulling everything apart. The consequences of dark energy are profound and terrifying. In the far future, it will tear apart everything we see. First, galaxy clusters will separate beyond recognition, becoming isolated islands in an ocean of expanding darkness. The light from distant galaxies will be stretched to wavelengths so long that they become undetectable. Our cosmic horizon will shrink, leaving our own galaxy alone in an empty, black universe. Then, as the expansion continues to accelerate, individual galaxies will lose their ability to hold together against the cosmic tide. Stars will be stripped from their orbits, their light fading into the growing darkness. Eventually, even atoms themselves may be stretched apart in what scientists call the Big Rip. Stars will be extinguished, planets will drift away from their suns, and even the fundamental particles that make up matter will be separated by vast, uncrossable distances. Dark energy, which seems gentle today, will become the universe's final destroyer, unmaking everything that gravity and the other forces worked billions of years to create. It is a slow, patient apocalypse, a cosmic unraveling that will leave behind a cold, dark, and empty universe. The ultimate victory of emptiness over structure, of expansion over attraction. The final, silent end of everything we know. Imagine taking a mountain and compressing it down to the size of a sugar cube. The result would still be 1,000 times less dense than a neutron star. These cosmic lighthouses pack the mass of our sun into a sphere just 12 miles wide, creating gravitational fields so intense they warp light itself and bend space-time into impossible geometries. But gravity is not their most terrifying feature. Neutron stars possess magnetic fields 1 trillion times stronger than Earth's protective magnetosphere. These invisible force fields trap charged particles and accelerate them to nearly the speed of light, creating beams of radiation that sweep across space like cosmic searchlights. The magnetic field of a typical neutron star is so powerful it could erase every credit card on Earth from a distance of 600 miles. If you could somehow approach within 1,000 kilometers, the magnetic force would be strong enough to pull the iron from your blood. The field lines themselves become visible as they trap and channel streams of charged particles into narrow beams. When these magnetized neutron stars spin, they become pulsars, firing beams of radio waves and X-rays with the precision of atomic clocks. Some rotate 600 times per second, faster than a kitchen blender, yet maintain perfect timing that rivals the most accurate timepieces ever built. Each pulse marks another rotation of a stellar corpse spinning in the darkness. The surface of a neutron star is a realm of impossible physics where familiar matter cannot exist. The magnetic field is so strong, it stretches atoms into needle-like shapes aligned with the field lines. Normal atomic structure breaks down completely, replaced by exotic forms of matter that exist nowhere else in the universe. Any ordinary matter that falls onto a neutron star's surface would be compressed instantly into a layer just millimeters thick. The gravity is so intense that a marshmallow dropped from waist height would hit the surface with the force of a hydrogen bomb, releasing more energy than all the explosives used in World War II. Some neutron stars, called magnetars, have magnetic fields 1,000 times stronger still, approaching the maximum strength allowed by the laws of physics. When these objects experience magnetic quakes, their crusts crack and shift, releasing more energy in 1/10 of a second than our sun produces in 100,000 years. These magnetic cataclysms create giant flares that can be detected from across the galaxy. The most powerful magnetar flare ever recorded temporarily affected Earth's upper atmosphere from a distance of 50,000 light-years, demonstrating the incredible reach of these stellar remnants. The magnetic field around a magnetar is so intense that it affects the vacuum of space itself, causing it to become birefringent, like a crystal. Light waves become polarized as they pass through this magnetized void, providing astronomers with direct evidence of field strengths that exceed anything achievable in terrestrial laboratories. But these stellar remnants are only the beginning of nature's most extreme creations. Stretching across the observable universe are invisible threads that could slice through planets like wire through cheese. These cosmic superstrings, if they exist, are one-dimensional objects thinner than a proton, but potentially longer than galaxy clusters. They are scars left over from the birth of the universe itself, marking phase transitions in the fundamental structure of space-time. According to string theory, cosmic strings formed during the first fraction of a second after the Big Bang, when the universe underwent rapid changes in its fundamental properties. They are like cracks in a frozen pond, marking the boundaries where different regions of space crystallized in slightly different ways as the cosmos cooled from its initial state of perfect symmetry. A cosmic string just 1 meter long would weigh as much as Earth. Yet these objects are so thin, they are essentially one-dimensional, having length but no width or height in the conventional sense. They exist at the very boundary between existence and nothingness, matter and energy, reality and pure mathematics made manifest. The energy contained within a cosmic string is almost incomprehensible. A string spanning the distance from Earth to the Moon would contain enough mass energy to power human civilization for trillions of years. Yet this enormous energy is concentrated in a line so thin that it has no measurable thickness, making cosmic strings the ultimate expression of energy density. If cosmic strings move through space, they create ripples in space-time itself, generating gravitational waves that could be detected by our most sensitive instruments. When two cosmic strings intersect, they can create loops that oscillate like guitar strings plucked by the hand of the universe itself, sending gravitational waves rippling outward at the speed of light. These cosmic string loops gradually lose energy through gravitational wave radiation, shrinking over time until they eventually disappear. Some scientists believe cosmic strings could act as cosmic highways, allowing faster-than-light travel through folded space. Others think cosmic strings might be windows into extra dimensions, hidden from our three-dimensional world. These theoretical monsters remain hidden in the mathematics of physics, waiting to be discovered or disproven by future observations. 4 billion light-years from Earth, a black hole the size of our solar system is launching a beam of particles that stretches across an entire galaxy. This jet of superheated plasma moves at 99.9% the speed of light, carrying enough energy to power 1 trillion stars while maintaining perfect focus across distances that dwarf human comprehension. Quasar jets are born in the chaos surrounding supermassive black holes, where space-time itself becomes a battlefield between gravity and magnetism. As matter spirals inward towards certain doom, it forms an accretion disk spinning at incredible velocities. Magnetic fields, amplified by the disk's rotation, become twisted into configurations that store enormous amounts of energy. These magnetic field lines act like cosmic particle accelerators, channeling material from the inner regions of the accretion disk into narrow beams that shoot outward from the black hole's poles. The same gravitational forces that should drag everything into oblivion instead launch some material back into space at relativistic speeds through this magnetic catapult mechanism. The jets are so straight, they appear drawn with a cosmic ruler held by divine hands. They maintain their narrow focus across distances of hundreds of thousands of light years, threading through space with precision no human technology could match. The particles within these jets carry energies millions of times greater than anything we can create in our most powerful particle accelerators on Earth. Individual protons race along the jet at speeds so close to light that their relativistic mass increases by factors of thousands, turning ordinary matter into cosmic bullets of incredible power. When a quasar jet points directly at Earth, we see it as a blazer, and the light appears to brighten and fade as the beam sweeps past us like a lighthouse. These blazers can vary in brightness by factors of hundreds within days or hours as turbulence in the jet creates bright knots of emission traveling toward us at apparent speeds faster than light itself. This faster-than-light motion is an illusion created by the geometry of observation. When material moving at 99% light speed travels almost directly toward us, it appears to cover vast distances in impossibly short times. The effect demonstrates just how close to the ultimate speed limit these cosmic jets actually travel. The most powerful quasar jets carry enough energy to heat entire galaxy clusters, blowing bubbles in the surrounding gas that persist for hundreds of millions of years. These cosmic blowtorches can prevent new stars from forming across regions spanning millions of light years, effectively sterilizing vast volumes of space. Recent observations have revealed jets that extend far beyond their host galaxies, stretching into the intergalactic medium where they continued to propagate for millions of years. These ancient jets carry the signature of black hole activity from cosmic epochs when the universe was younger and more violent than today. In a binary star system 30 million light years away, a white dwarf star is slowly stealing material from its companion, like a cosmic vampire feeding on stellar blood. For millions of years, hydrogen gas flows from the larger star onto the compact remnant, building up layer by layer like snow accumulating on a mountainside. But this stellar snowball is approaching a deadly threshold that will trigger one of the universe's most precise explosions. White dwarf stars are the dense cores left behind when sun-like stars exhaust their nuclear fuel and shed their outer layers. These stellar remnants pack the mass of our sun into a sphere the size of Earth, creating matter so dense that a teaspoon would weigh as much as a car. The stolen material accumulates on the white dwarf's surface, compressed by gravity into a thin shell of hydrogen that gradually builds up pressure and temperature. When the white dwarf reaches exactly 1.4 times the mass of our sun, something catastrophic happens. This critical mass, known as the Chandrasekhar limit, represents the maximum weight that electron degeneracy pressure can support. Beyond this point, the star can no longer hold itself up against its own gravity. The accumulated material ignites in a runaway thermonuclear explosion that tears the entire star apart in seconds. This is a Type Ia supernova, and it represents one of the most precisely violent events in the universe. Every Type Ia supernova releases almost exactly the same amount of energy because they all involve the same mass of material undergoing the same nuclear reaction. This cosmic standardization makes them perfect tools for measuring distances across billions of light years. The explosion shines with the light of 5 billion suns, visible from galaxies billions of light years away. For weeks, a single exploding white dwarf can outshine an entire galaxy. The explosion synthesizes and scatters elements essential for life across vast regions of space. The calcium in your bones, the iron in your blood, and the nickel in coins were all forged in the hearts of exploding white dwarf stars. You are literally made of stellar ashes, scattered by these cosmic crematoriums billions of years ago. Two city-sized objects spiraled toward each other through the darkness of space, locked in a gravitational death dance that has lasted for millions of years. They are neutron stars, the crushed cores of massive stars, and their collision will create the most violent event in the nearby universe, while forging elements more precious than anything in a king's treasury. Each neutron star contains more mass than our sun compressed into a sphere just 12 miles across. As they orbit closer and closer, the neutron stars distort each other's shapes through pure gravitational force. The orbital dance accelerates as energy bleeds away through gravitational waves, ripples in space-time that stretch and compress the very fabric of reality. Advanced detectors on Earth can measure these waves even though they change distances by less than 1/10,000th the width of a proton. In the final seconds before collision, the neutron stars complete hundreds of orbits per second. When they finally touch, they create a brief flash of gamma rays, followed by a longer-lived explosion called a kilonova. The merger forges elements heavier than iron through a process called rapid neutron capture. In the extreme conditions of the collision, atomic nuclei are bombarded with so many neutrons that they can barely absorb them fast enough. This creates unstable neutron-rich isotopes that decay into stable heavy elements, including gold, platinum, and uranium. A single neutron star merger produces quantities of gold equivalent to several Earth masses. The collision ejects this stellar treasure at speeds approaching 1/3 the speed of light, seeding nearby space with materials that will eventually find their way into future generations of planets and asteroids. The kilova light comes from billions of newly created atomic nuclei undergoing radioactive decay, creating a fireball that shines with the combined light of hundreds of millions of suns. 13.8 billion years ago, everything that exists today was compressed into a point smaller than a proton. All the matter and energy in the observable universe occupied a space with no dimensions at all. This was the Big Bang singularity, and it represents the ultimate expression of cosmic power, the moment when existence itself began. At this primordial moment, the laws of physics as we understand them break down completely. Temperature and density become infinite. Space and time have no meaning. The four fundamental forces were unified into a single, unimaginably powerful interaction. In the first fraction of a second, the universe expanded faster than light itself. This period of cosmic inflation stretched space by factors of billions in less time than it takes to blink. Space did not explode into pre-existing emptiness, but rather created new space as it grew. As the universe expanded and cooled, this cosmic unity shattered. The forces separated in a series of phase transitions that released enormous amounts of energy and determined the basic structure of physical law. First, gravity separated, then the strong force, and finally, electromagnetism split from the weak force. During the first minute, the universe cooled enough for the first atomic nuclei to form through a process called Big Bang nucleosynthesis. Protons and neutrons fused together in a cosmic forge that created most of the hydrogen and helium we see today. For 300,000 years, the universe remained opaque to light, a glowing fog filled with energy. Then came cosmic dawn. Electrons and atomic nuclei combined to form the first neutral atoms, allowing light to travel freely for the first time. This cosmic clearing created the afterglow we still see today as the cosmic microwave background radiation, a faint echo of creation itself. Beyond the realm of ordinary supernovae lies something far more violent. When a star containing 50 times the mass of our sun finally runs out of nuclear fuel, it creates a hypernova, an explosion so energetic it dwarfs regular supernova by factors of 10 to 100. Only the most massive, rapidly rotating stars can trigger hypernovae. When the core of such a star collapses, it forms a black hole almost instantly. The star's rapid rotation creates an accretion disk around the newborn black hole, generating magnetic fields of unimaginable strength. These twisted magnetic field lines launch jets of matter and energy outward at 99.9% the speed of light. The jets bore through the collapsing star like cosmic drill bits, carrying enough energy to power our sun for billions of years. The shock wave from the jet's passage heats the star's interior, triggering explosive nuclear burning throughout the stellar remnant. A single hypernova can synthesize more heavy elements than dozens of normal supernovae, scattering them across vast regions of space. Their shock waves can disrupt star formation across entire regions of galaxies. Two massive galaxy clusters race toward each other at speeds of thousands of miles per second. When these cosmic titans collide, they create the most energetic events in the universe since the Big Bang itself. Galaxy clusters are the largest gravitationally bound structures in the cosmos. When they collide, the energy released exceeds the combined output of all the stars in both clusters by factors of 1,000,000. The hot gas that fills the space between galaxies slams into each other at velocities approaching 5,000 miles per second. The collision creates shock waves that heat the gas to temperatures exceeding 100 million degrees. These cosmic crashes can trigger the formation of radio halos spanning millions of light years and bow shocks that propagate outward at thousands of kilometers per second. During the collision, individual galaxies experience their own violent encounters. Tidal forces can strip stars from galaxy outskirts, creating long streams of stellar debris. Hidden in the quantum foam that underlies all reality, lurks a possibility so terrifying that it could end everything we know in an instant. The Higgs field, which gives all particles their mass, might not be in its lowest possible energy state. If this field suddenly dropped to its true minimum, it would create a bubble of destruction that expands at light speed, rewriting the laws of physics and annihilating everything in its path. The Higgs field permeates every corner of space, like a ball balanced on a hill. This field might currently sit in what physicists call a false vacuum state. It appears stable, but it could potentially roll down to an even lower energy level. If vacuum decay began anywhere in the universe, it would create an expanding sphere of true vacuum moving outward at exactly the speed of light. Nothing could escape. We would have no warning. Inside the bubble of true vacuum, the fundamental constants of nature would be different. Particles might have different masses or not exist at all. Atoms as we know them could not form. Chemistry and biology would become impossible. The energy difference between the false vacuum and true vacuum would be released as the bubble expanded, exceeding the rest mass energy of all matter in the universe. Current calculations suggest that our vacuum might indeed be metastable. High-energy events like cosmic ray impacts or black hole evaporation could potentially trigger the transition. Even quantum fluctuations might spontaneously nucleate a bubble of true vacuum in empty space. The terrifying aspect of vacuum decay is its inevitability if the false vacuum state exists. Quantum mechanics guarantees that any metastable state will eventually decay. Over the vast timescales of cosmic evolution, even the most unlikely events become certain. Vacuum decay would be the ultimate cosmic reset button. Everything would be erased and replaced by a universe with fundamentally different physics in the first moments after the Big Bang. Tiny fluctuations in density could have collapsed to form black holes more massive than mountains, yet smaller than atoms. These primordial black holes would possess gravitational fields so intense they warp space and time on scales invisible to the human eye. Unlike black holes formed from collapsing stars, primordial black holes could have any mass. The smallest ones would be quantum objects, where the strange rules of quantum mechanics clash with the absolute authority of general relativity. A primordial black hole with the mass of a mountain would be smaller than a proton. According to Stephen Hawking's calculations, black holes emit radiation and slowly evaporate over time. The smaller the black hole, the faster it evaporates and the more violently it dies. A primordial black hole with the mass of a large asteroid would explode with the energy of millions of hydrogen bombs. In its last second of existence, it would release more energy than our sun produces in an entire year, all concentrated in a point smaller than an atomic nucleus. If primordial black holes exist in large numbers, they could solve one of cosmology's greatest mysteries, the nature of dark matter. These invisible objects would exert gravitational influence without emitting light. The most massive primordial black holes could have served as seeds for the supermassive black holes we observe at the centers of galaxies today, solving the puzzle of how such enormous black holes could have formed so early in the universe's history, before the universe was even 1 second old. Space itself underwent the most violent expansion in cosmic history, in a period shorter than the time it takes light to cross a proton. The universe grew from smaller than an atom to larger than a grapefruit. This process, called cosmic inflation, represents the most powerful force ever unleashed, stretching space faster than the speed of light. The driving force was a quantum field called the inflaton, which filled all of space with an enormous energy density. Unlike normal matter, this field had the bizarre property of creating more energy as space expanded. Inflation solved several fundamental problems. It explains why the cosmic microwave background radiation has nearly identical temperatures in all directions. Quantum fluctuations in the inflaton field were stretched to cosmic scales, creating the density variations that would later grow into galaxies and galaxy clusters. When inflation finally ended, the inflaton field decayed into ordinary matter and radiation, reheating the universe to temperatures exceeding 10 to the 28th degrees. Some theories suggest that inflation is an eternal process that continues to create new regions of space-time beyond our observable universe. In this scenario, our entire cosmos might be just one bubble in an infinite multiverse where new universes are constantly being born. In the heart of a dying star, spinning at 1,000 revolutions per second, magnetic fields 1 trillion times stronger than Earth's are about to unleash destruction beyond imagination. This is a magnetorotational supernova, where the combination of extreme rotation and magnetic power creates explosions that dwarf even the mightiest gamma-ray bursts. When the most massive, rapidly rotating stars collapse, the conservation of angular momentum spins the core even faster. As the stellar core shrinks from the size of Earth to just 12 miles across, its rotation rate increases by millions of times. The magnetic field lines, frozen into the collapsing plasma, become twisted and amplified until they reach strengths that approach the theoretical limits allowed by physics. These fields become so powerful they can influence the structure of space-time itself. When these magnetic structures finally become unstable and reconnect, they release their stored energy in violent magnetic explosions. The combination of rapid rotation and extreme magnetic fields creates a cosmic dynamo more powerful than anything else in the universe, launching jets of magnetized plasma at velocities approaching the speed of light. The magnetic fields generated are so strong they affect the vacuum of space itself, causing it to become birefringent, splitting light into separate polarizations. Space itself becomes a kind of cosmic crystal with directional properties. The energy released by a magnetorotational supernova can exceed that of a normal supernova by factors of hundreds, synthesizing exotic isotopes that cannot be created under any other conditions. In the vast halos surrounding every galaxy, an invisible substance outweighs all the stars by a factor of 5 to 1. This dark matter feels gravity, but interacts with nothing else we understand, creating a shadow universe. But if dark matter particles ever encounter their antimatter twins, they could unleash explosions that make supernovae look like fireflies. Dark matter particles, if they are their own antiparticles, would annihilate completely when they collide, converting their entire mass into pure energy. A single kilogram of dark matter undergoing annihilation would release the same energy as 21 million tons of explosives. In the dense cores of galaxy clusters, where dark matter concentrations reach their peak, these annihilation events could create cascades of high-energy particles and gamma rays, exceeding the combined output of all the stars in the cluster. The annihilation process could create pairs of photons with energies millions of times greater than visible light. These gamma rays would carry the signature of dark matter destruction, providing a direct window into the properties of this mysterious substance. In the extreme environment near black holes, where dark matter densities can reach extraordinary levels, annihilation rates could become so high that they contribute significantly to the total energy output. The search for dark matter annihilation signals has led astronomers to examine the most extreme environments in the universe. The absence of clear signals so far suggests that either dark matter does not self-annihilate or the process occurs much more rarely than initially predicted. Somewhere in the depths of space, protons are being accelerated to energies that dwarf anything we can achieve on Earth. These cosmic ray particles race through the galaxy at 99.9999% the speed of light, carrying individual energies equivalent to a baseball thrown at 60 miles per hour, compressed into a single atomic nucleus. The most energetic cosmic rays detected on Earth carry energies exceeding 10 to the 20th electron volts, more than 10 million times the energy achievable in the Large Hadron Collider. The cosmic accelerators responsible for these extreme particles remain one of astrophysics' greatest mysteries. Active galactic nuclei, powered by supermassive black holes, represent the most likely candidates. The magnetic fields near these objects can store enormous amounts of energy, launching jets that create natural particle accelerators millions of light years long. The most extreme cosmic ray events might involve entirely different acceleration mechanisms. Some theories suggest that the decay of exotic particles left over from the Big Bang could produce cosmic rays with energies exceeding anything possible through conventional acceleration. In the apparently empty space between atoms, between planets, between stars, the quantum vacuum seethes with invisible activity. Virtual particles pop into existence and annihilate each other in time so brief they exist below the threshold of direct observation. Yet these quantum fluctuations contain enough energy to power the entire observable universe. The quantum vacuum is not truly empty, but filled with zero-point energy that exists even at absolute zero temperature. Calculations suggest that the energy density of quantum vacuum fluctuations should be 10 to the 120th times larger than the observed energy density of the universe. This enormous discrepancy, known as the cosmological constant problem, represents one of the greatest failures of theoretical physics. Yet quantum vacuum fluctuations do produce measurable effects. The Casimir effect demonstrates that two metal plates placed very close together will be pushed toward each other by the pressure of virtual particles. Virtual particles near the event horizons of black holes can become real through Hawking radiation. In the early universe, quantum vacuum fluctuations were stretched to cosmic scales during inflation, becoming the seeds of all large-scale structure. Some theories suggest that our entire universe originated from a quantum vacuum fluctuation, a brief deviation from nothingness that somehow became permanent. Beyond the edge of our observable universe, beyond the most distant galaxies we can ever hope to see, lies something that dwarfs all the cosmic forces we have encountered. If the multiverse exists, our entire universe, with all its supernovae, black holes, and gamma-ray bursts, becomes nothing more than a single bubble in an infinite ocean of realities. In the eternal inflation scenario, our Big Bang was not a unique event, but one of countless explosions occurring continuously throughout higher dimensional space. New universes are constantly being born as quantum fluctuations trigger inflation in regions of false vacuum. Each universe within this multiverse could have completely different fundamental constants. In some, gravity might be stronger or weaker. In others, the electromagnetic force might have different strength, making atoms impossible. The total energy contained within an infinite multiverse would literally be infinite. Some regions of the multiverse might contain universes that expand forever, while others collapse back on themselves in big crunches. In certain interpretations of quantum mechanics, the multiverse consists of all possible outcomes of quantum measurements existing simultaneously in parallel realities. Every time a quantum event occurs with multiple possible results, the universe splits into separate branches. The anthropic principle suggests that we observe our universe's particular combination of physical constants, because only this combination allows observers like us to exist. In a multiverse containing all possible combinations, conscious beings would necessarily find themselves in universes capable of supporting consciousness. We have journeyed from the quantum realm to the infinite multiverse, witnessing forces that stretch the very limits of what reality can contain. The most remarkable truth we have discovered is that the universe does not simply contain power. It is power. Every atom in your body exists because forces beyond imagination hold it together. Every star that lights the cosmic darkness burns because nuclear forces convert matter into pure energy. Every galaxy spins through space because gravity and dark energy wage their eternal war. But perhaps the most profound realization is that we, as conscious observers, are not separate from these cosmic forces. We are their direct products. The calcium in our bones was forged in stellar explosions. The iron in our blood was scattered by dying stars. The gold in our jewelry was created when neutron stars collided. We are literally made of stardust, assembled by forces so powerful they can create and destroy entire worlds. Yet here we stand, conscious beings capable of contemplating our own cosmic origins. Proof that the universe's greatest power may not be its ability to destroy, but its capacity to create complexity, beauty, and ultimately, awareness itself. The universe has been working for 13.8 billion years to create the conditions necessary for you to exist. Every force we have explored played a role in bringing about this moment. What is the most powerful thing in the universe? Perhaps it is not any single force, but the universe's inexhaustible creativity. Its ability to transform simple hydrogen into stars, stars into heavy elements, elements into planets, and planets into the stage where life and consciousness can emerge to contemplate the very forces that brought them into being. The universe's most powerful force may ultimately be its capacity to know itself through beings like us. In understanding cosmic power, We become the universe awakening to its own magnificent potential.
Imagine a voice so ancient that it speaks not in words, but in vibrations rippling across the void. No sound touches your ears, yet the universe resounds. You are lying beneath a canopy of stars, still and silent. But overhead, reality is anything but quiet. The night sky is an active symphony, bursting with stories that traverse billions of years. It is the place where time stretches, where gravity bends, and where light becomes a messenger from forgotten epochs. Every photon from a distant star is a time traveler. When it touches your eye, you are not seeing that star as it is, but as it was 10, 100, a billion years ago. Starlight does not merely illuminate, it testifies. What you see is a fossil record in the medium of light. Yet the universe's most haunting music doesn't ride on sound waves. In the vacuum of space, traditional sound cannot travel, but the cosmos still sings. It sings in electromagnetic radiation, in gamma rays, X-rays, ultraviolet and radio waves. These signals, translated by radio telescopes, tell us of spinning neutron stars, the collapse of suns, and the faint hum of the infant universe itself. You are in the control room now. Massive radio dishes point to the sky. On the monitors, rhythmic pulses appear. These are pulsars, neutron stars spinning hundreds of times per second, each one the collapsed core of a supernova. They emit radiation with such perfect timing that we use them to keep our atomic clocks in check. The death of a star becomes the heartbeat of our civilization's measurements. Then there are the irregular voices, bursts of radio waves from quasars, from the twisted spacetime near black holes, from the explosive births and deaths of stars. Some are steady, others are frantic. Each tells of extreme gravity, magnetic storms, and matter behaving in ways we still struggle to model. One of the universe's oldest sounds is the cosmic microwave background, faint radiation emitted just 380,000 years after the Big Bang. It pervades the universe, a leftover glow from a time before stars, before galaxies, before elements as we know them. It is the cosmic echo of the universe becoming transparent for the first time. Listen closer. Hydrogen, the most abundant element, speaks too. When it flips its electron's spin, it emits radio waves at a very specific frequency. With this, we map galaxies. We see where stars are born. We trace spiral arms. Interstellar gas clouds are not silent. They tell us where new suns will blaze into being. And our own star, the sun, is a wild instrument. It flares, it storms, it disrupts satellites and sparks auroras. It sends out coronal mass ejections, billion-ton clouds of plasma that can knock out power grids. It hums with activity beneath its surface, vibrating in oscillation modes we can detect. None of this is chaos. It is symphony. Patterns within patterns. Harmonies buried in noise. Chaos becomes data. Data becomes meaning. And yet, among all these signals, we hear whispers of something more enigmatic, something we cannot see but whose influence is overwhelming. Galaxies spin faster than they should. Light bends more than expected. A hidden force holds galaxies together. We call it dark matter. Dark matter is not just an absence, it is a presence without visibility. It neither emits nor absorbs light, but it has mass. It has gravity. It shapes the universe. In the 1970s, Vera Rubin noticed stars orbiting galaxies too quickly. They should have been flung into space, but they weren't. Something invisible kept them bound. That something dark matter makes up about 27% of the universe. We only see the scaffolding it creates. Imagine a dance, with visible stars and gas swirling around a phantom partner. The dancers move to music we cannot hear, led by something that eludes all senses but gravity. We map this dark matter by observing how it bends light, a process called gravitational lensing. Light from distant galaxies is curved, magnified, and split by mass we cannot detect, as if space-time itself is a warped mirror. There are theories. WIMPs, weakly interacting massive particles, are one candidate. These particles might pass through your body by the billions every second, unnoticed. Or maybe it's axions, exotic low-mass particles. Or perhaps it's not particles at all. but tiny primordial black holes born in the earliest seconds after the Big Bang. Underground detectors wait in stillness. They sit deep in old mines or under mountains, shielded from cosmic rays, waiting for a single particle of dark matter to collide with a nucleus and leave a trace. So far, silence. But silence in science is not failure. It is patience. It is readiness. It is knowing that absence can speak. The search continues. Each non-detection is a refinement, a narrowed path through the thickets of theory. And above, the stars go on spinning. Galaxies keep their form. The unseen hand persists, as if space itself remembers a shape we cannot yet recognize. Meanwhile, we move toward the most extreme place known to physics, the black hole. Born from the death of massive stars, black holes are regions of such density that space-time caves in on itself. A singularity lies at their core: infinite density, zero volume. Around this point is the event horizon, the boundary beyond which nothing returns. Time behaves strangely near a black hole. To an outside observer, anything falling in seems to slow, to freeze. But for the falling object, time ticks as usual. Cross the event horizon, and all paths lead inward. Some black holes are stellar mass, formed from collapsed stars. Others are giants, millions to billions of solar masses lurking at the centers of galaxies. Sagittarius A, the supermassive black hole at the heart of the Milky Way, anchors our galaxy. Our solar system orbits it every 230 million years. In 2019, we saw the silhouette of a black hole for the first time. Not directly, but by imaging its glowing accretion disk matter spiraling in, heating to billions of degrees. The Event Horizon Telescope, a global array of radio observatories, gave us a picture of the M87 black hole, a bright ring around a shadow. And black holes do not live forever. Stephen Hawking predicted they emit faint radiation. Hawking radiation due to quantum effects. Over immense timescales, they will evaporate. The cosmos will grow dimmer, quieter. But not yet. Not today. For now, the universe still roars, even in its darkest corners. The distant moon hung low over the Martian horizon, a pale sliver against the rust-red dust. As the first explorers set their instruments in the soil, here, at the boundary of Earth's influence, a new perspective began to form. Beneath the planet's thin sky, stripped of a protective magnetosphere, the silence was not just auditory, it was existential. This was not Earth extended. It was something else, something wholly alien. The dust underfoot had not shifted for millions of years. Each grain was a relic, untouched by rain or running water, shaped only by the breath of thin winds and ancient impacts. And yet, in this stillness, a new kind of motion was born, not of rock or weather, but of thought. What would it mean to build a human presence on Mars? Could our minds, wired for forests and oceans, adapt to crimson plains and twin moons? The cosmos is not built to accommodate human need, but neither is it hostile in any deliberate way. It is indifferent, and in that indifference, there is a peculiar freedom. Mars, though often imagined as a dry, frozen desert, tells a richer tale. Evidence of past rivers, of ancient lakes, even of possible oceans, lies in the sinuous channels etched into its surface. Clay deposits, which only form in the presence of water, whisper of epochs when Mars was blue. And if it once held water, could it have once held life? The question is not trivial. It pushes against the boundaries of biology. Life, we now know, can exist in boiling sulfur springs, in the vacuum of space, in clouds of acid. Why not in the subterranean aquifers of an ancient Mars? To search for life is to search for connection, not merely in the microbial sense, but in the recognition that we are not a singular cosmic accident. If life emerged independently on Mars, even once, it would mean the universe is fundamentally inclined toward complexity, toward pattern, toward awareness. From orbit, Mars reveals scars of cataclysm volcanoes like Olympus Mons, the tallest in the solar system, and Valles Marineris, a canyon system that dwarfs Earth's Grand Canyon. These formations speak of forces vast and violent. They also remind us that Mars is not dead. It slumbers. Seismic activity and strange methane emissions hint at processes still ongoing beneath its crust. Perhaps it is not a world frozen in time, but one caught mid-transition. The journey beyond Mars takes us into realms of scale that bend comprehension. Past the asteroid belt, where Ceres, a dwarf planet, lurks as a forgotten embryo of planetary formation, we enter the realm of the gas giants. Jupiter, with its churning bands of storm and radiation belts, guards the solar system like a gatekeeper. Its gravity shapes the orbits of comets, shepherds asteroids, and may have shielded Earth from countless impacts. Yet it is not just a protector. Within its orbiting moons lie some of the most promising places to search for life beyond Earth. Europa, with its cracked icy shell, likely hides a liquid ocean beneath, warmed by tidal flexing. Ganymede, the largest moon in the solar system, possesses a magnetic field and anomaly among moons and hints at subsurface oceans of its own. Saturn's Enceladus ejects plumes of salty water and organic molecules from geysers near its south pole. These are not dead rocks. They are worlds in waiting. Each of these icy bodies challenges our terrestrial assumptions. On Earth, life clings to thermal vents on the ocean floor, independent of sunlight. Might similar ecosystems thrive in the dark seas of Europa or Enceladus? If so, the universe might teem with biology not in Earth-like temperate zones, but beneath frozen shells, in the warmth of tidal embrace. Uranus and Neptune, the ice giants, bring new mysteries. Their atmospheres swirl with exotic chemistry, and their magnetic fields tilt wildly from their rotational axes. Neptune's moon. Triton orbits backward, a clue to its captured origin, and geysers of nitrogen vent from its crust. These outer worlds are not merely far, they are strange in ways that challenge both instruments and imagination. Beyond them lies the Kuiper Belt, a realm of frozen remnants, including Pluto, whose demotion from planetary status obscures its intricate geology and possible internal ocean. The New Horizons mission revealed a heart-shaped basin of nitrogen ice and mountains of water rock. Even here, at the edge of sunlight, geology speaks. And then, at last, the heliopause, the boundary where the solar wind yields to the interstellar medium. Voyager 1 crossed it in 2012, becoming the first human-made object to enter interstellar space. Its golden record, bearing music and messages from Earth, floats onward into the dark, a whisper of sentience hurled into the abyss. What does it mean to extend our senses so far? To know, with certainty, that we have sent artifacts and perhaps soon, people beyond the nursery of Earth. It is not conquest, it is communion. The search for alignment with forces larger than ourselves. The impulse is not to dominate, but to understand. In the silence beyond planets, where only photons and particles drift, our thoughts continue. About time, about death, about continuity. When we plant a flag or a sensor, it is not to say we own this, but to declare we noticed. It is a profoundly humble act. The solar system is a cathedral of time and physics. Each moon, each orbit, each cratered surface is a chapter in a book older than humanity. And we, with our instruments and questions and dreams, are its youngest readers. But beyond reading, we may someday write, leave traces not only of biology, but of poetry, logic, compassion, a lander's medal, a rover's track, a human footprint pressed into Martian soil, not noise, but meaning. In the faint light of a distant sun, the first greenhouse might bloom, the first cry might echo in a dome, not as colonizers, but as participants in a story that is still being told. Imagine drifting through the frozen edge of our solar system, past the orbits of Neptune and Pluto, into the Kuiper Belt, where icy relics from the birth of the sun still orbit in their ancient paths. Here lie the dwarf planets, comets, and countless icy rocks that whisper of a primordial time. It is a silent realm, barely touched by sunlight, where time seems to stretch and celestial mechanics dance in slow motion. As you pass through, your gaze is drawn toward the mysterious Oort cloud, a hypothetical shell of icy objects far beyond the planets, stretching halfway to the nearest stars. If a comet begins its long journey toward the sun, it may have originated here, perturbed by the gravity of a passing star or a ripple in the galactic tide. The outermost reaches of our solar system mark the boundary between the known and the speculative. This is where gravitational dominion gives way to interstellar drift. Out here, the solar wind fades, and the heliopause, our sun's final breath, meets the interstellar medium. Beyond this invisible threshold lies the vast ocean of the galaxy, populated by rogue planets, errant comets, and the interstellar gas from which stars are born. Each particle of dust out here is a relic older than any terrestrial stone, untouched since the galaxy's youth. Our journey now moves inward, not in space, but in scale. We dive beneath the surface of understanding, into the infinitesimal heart of matter. Everything you see, touch, and know is made of atoms, billions of them dancing in patterns too small to perceive. Each atom contains a nucleus, a dense core of protons and neutrons, surrounded by a ghostly cloud of electrons. But even these subatomic particles are not fundamental. Inside protons and neutrons reside quarks, held together by gluons in a dynamic tension described by quantum chromodynamics. Quarks, electrons, neutrinos. These are the building blocks of the universe, governed by the rules of the standard model of particle physics. It is our most successful framework for understanding matter and its interactions. Yet, it is also incomplete. It says nothing of gravity, of dark matter, or of the strange imbalance between matter and antimatter. Physicists search for unification, a deeper layer of reality where all forces merge, where the universe writes its rules in simpler terms. To probe this hidden structure, scientists use colossal machines, particle accelerators like the Large Hadron Collider. These vast rings hurl particles to near light speed and smash them together, recreating conditions just moments after the Big Bang. From the debris of these collisions, we discovered the Higgs boson, a particle that gives mass to others through a field that permeates all of space. It is like an invisible molasses through which everything must pass. But even the Higgs, profound as it is, does not answer every question. What stabilizes the mass of the Higgs itself? Could supersymmetry provide the answer, positing partner particles for every known one? Or might string theory hold the key, suggesting that all particles are different vibrations of tiny strings existing in 10 or 11 dimensions? These ideas remain unproven, beautiful, but elusive. The closer we look, the more the universe begins to resemble a question. Is space-time itself granular, made of discrete units smaller than any atom? Some physicists believe in loop quantum gravity, a model where space and time emerge from networks of interconnections, quantum threads woven into the cosmos. Others ponder the holographic principle, which suggests that everything we experience in 3 dimensions is encoded on a distant 2-dimensional surface, like a cosmic projection. And what of time? Is it an arrow, always pointing forward, or an illusion born from entropy? The laws of physics are mostly time-symmetric. They work just as well in reverse. Yet, our experience of time is not symmetric. We remember the past, not the future. Entropy, the measure of disorder, increases. This is the one true direction time seems to follow. But why did the universe begin in a state of such low entropy? Why was it so ordered at its birth? Perhaps the most profound mysteries lie not in the stars, but in the silent intervals between them, in the gaps of our knowledge, in the stillness where science meets philosophy. The cosmos is not just a place of planets and particles. It is a stage where meaning, consciousness, and curiosity come to life. We, the observers, are also part of the experiment. As we float back from the microscopic into the vastness again, we carry with us the recognition that we are not separate from the universe, we are of it. Each atom in your body was forged in the heart of a star. Each breath echoes cycles of carbon and oxygen that have danced through 1,000 forms. The universe dreams through us, and in contemplating it, we allow it to know itself. The edge of the solar system, the edge of matter, the edge of certainty. These are not limits, but invitations, reminders that exploration begins when we dare to ask the questions that have no easy answers. 100,000 light-years from end to end. The Milky Way is a structure vast enough to contain billions of stories, and yet it is only one galaxy among countless others. Its spiral arms hold a history of cosmic birth, violence, and evolution. But even in its grand design, our vantage point remains constrained. We look from the inside out. Our solar system nestled in one quiet fold of the Orion Arm, orbiting the galactic center like a boat gently circling the eye of a storm. The stars above seem eternal, yet they too move, pulled by invisible currents, sculpted by forces we cannot touch. Each one participates in a vast celestial choreography. It takes the Sun 230 million years to complete just one galactic orbit. In that time, entire species have risen and vanished on Earth. The dinosaurs lived and died without completing a single cosmic lap. Now, under the night sky, we follow their path with radio telescopes and digital star charts. Beyond the spiral arms lie stellar halos and globular clusters, ancient, spherical groupings of stars orbiting the galaxy like bees around a hive. These clusters are fossils, containing stars almost as old as the universe itself. Studying them is like peering into a cosmic archive, unlocking information about the galaxy's adolescence. Their orbits are wild and elliptical, often slicing through the galactic disk. Their presence hints at collisions, past galactic mergers that left behind structural echoes. We now know the Milky Way is on a slow, inevitable collision course with the Andromeda Galaxy. In roughly 4.5 billion years, the two spirals will begin to interact. Their stars will mostly pass without colliding, like dust motes blown through one another. But gravity will stretch and warp the galaxies into streamers of stars. The final product will be an elliptical galaxy, swollen and slow. Some call it Milkomeda. It will be a new home for old stars. But galaxies aren't just stellar cities. They are governed by dark matter halos invisible, massive envelopes that dictate the galaxy's structure and motion. These halos are not decorative. They are architectural. Without them, spiral arms would fly apart. The visible galaxy is just the skin of a much deeper, invisible anatomy. Within this scaffolding, gravity sculpts matter into patterns and forms that are replicated across the cosmos. These structures form filaments, walls, and voids the cosmic web. On the grandest scale, the universe resembles a neural network, with galaxies as nodes connected by filaments of dark matter and gas. Between these filaments lie immense voids, where few galaxies dwell. These are the deserts of the cosmos, vast stretches of near-nothingness. If you could step back far enough to see the web in full, you might feel as if you were gazing at a living organism. Yet this structure is dynamic. Superclusters slowly drift, galaxy clusters merge, and quasars, supermassive black holes at galactic cores, send jets of particles through intergalactic space. These active galactic nuclei are among the brightest phenomena in the universe. They burn with energy drawn from the innermost orbits of matter, spiraling toward gravitational oblivion. Their light travels billions of years to reach us, a testament to power born from collapse. Instruments like the James Webb Space Telescope now peer into these deep structures, capturing light from the earliest galaxies. It sees not just the glow of stars, but the spectral fingerprints of their composition: oxygen, carbon, even water vapor in nascent planetary systems. We are watching the universe watch itself become. In this light, we begin to glimpse not only what the cosmos is, but what it has the potential to be. As we trace these immense structures, the arrow of time continues its slow cosmic march. Thermodynamics tells us that entropy increases, order becomes disorder. Galaxies will eventually run out of fuel, their stars dimming, their matter decaying. But the story doesn't end with extinction. Matter that once formed stars and life will disperse, contributing to new structures. Nothing is wasted in the cosmos, everything transforms. On some distant day, when the last star flickers out and black holes begin their long evaporation via Hawking radiation, the universe may reach a state of maximum entropy, a diffuse, dark sea of particles and fading remnants. But even then, the laws of physics persist, whispering through silence. The universe remembers its origins not in memory, but in structure. And yet, across this vastness, the spark of inquiry continues. From a small blue planet on the edge of a minor spiral arm, consciousness has risen that dares to ask where it came from and what might lie ahead. We are not mere observers. We are participants in a universe still in the act of becoming. The Earth rotates slowly beneath a sky full of secrets, and as dawn begins to stain the horizon with soft light, the final frontier we've been tracing reveals yet another boundary, not of matter, nor of space, but of understanding itself. Human cognition, our curiosity, our fears, our models is the last telescope we aim outward and inward. In the midst of distant galaxies and decaying stars, the very idea of intelligence demands attention. Intelligence is not just a feature of biology, it may be an emergent property of matter, given time, complexity, and the right constraints. Earth may be a proof of concept, but if minds can emerge here, why not elsewhere? Could galaxies be learning systems? Could consciousness, somehow, be entangled with cosmology itself? We usually think of intelligence as a late evolutionary development, a tool for navigation, tool-making, storytelling. But consider the possibility that intelligence is also a cosmic phenomenon, an entropy negotiator, a meaning maker in an otherwise indifferent expanse. Some physicists speculate that life, and perhaps intelligence, could serve as a counterbalance to entropy, shaping order even as the universe trends toward thermal equilibrium. In this framework, every self-aware being becomes a node of resistance, a flicker of coherence against the pull of chaos. And every question we ask about the universe is the universe, in a sense, asking itself. Now imagine a future where intelligence becomes not just biological but cosmic in scale. Civilizations, if they survive their infancy, may begin reshaping not just planets, but stars. Dyson spheres, hypothetical megastructures encasing stars to capture their full energy output, are one example. We haven't detected any yet, but our searches for Type 2 civilizations, those capable of harvesting the energy of entire stars, or Type 3 civilizations that manipulate galaxies, continue. If they exist, they're subtle, or they've transcended detectable physicality altogether. Perhaps intelligence eventually merges with space-time structure, embedding itself as information gradients, quantum echoes, gravitational imprints. And if civilizations collapse as ours might, they still leave behind artifacts of thought, radio waves sent eons ago, gravitational lensing patterns from abandoned stellar engines, the final memory of a thinking species encoded in the rotation of a neutron star. But even if we are alone uniquely aware in an otherwise quiet cosmos, our awareness may be enough. To observe the universe is to become part of its unfolding. Just as measurement changes the state of a quantum system, consciousness alters the narrative trajectory of the cosmos. And what of the end? What awaits when the stars burn out, when black holes evaporate, when entropy finishes its slow, patient erasure? The far future of the universe is an austere place, cold, dark, sparse, but some speculate that information might never be entirely lost. The universe, even in its final state, could remain a container of memory. Through theories like the holographic principle, where the three-dimensional world is described by two-dimensional information at its boundary, we begin to glimpse a reality where space, time, and matter are all emergent properties of deeper informational structures. Some go further still, proposing that the universe itself is a kind of computation, not metaphorically, but literally a quantum process unfolding across dimensions. From this perspective, our thoughts, our dreams, our efforts to understand the stars are operations in a grander algorithm whose purpose we may never decode. Still, we calculate, we remember, we imagine. And imagination is no small thing. It is the propulsion of science, the architecture of empathy, the poetry of discovery. Through imagination, we transcend the here and now, projecting ourselves into alien atmospheres, lost epochs, and speculative futures. As we continue this cosmic journey, we must also face the mirror. The tools of astronomy, cosmology, and particle physics have given us unprecedented power but also deep responsibility. What we do with this knowledge will shape not just our destiny, but the future of sentient matter in this corner of the universe. How we handle climate instability, resource depletion, artificial intelligence, and our interdependence with ecosystems will determine if we're a long-lived civilization or a brief spark in galactic time. The stars will go on, but whether we remain to witness them is not guaranteed. Even the act of looking up, so simple, so ancient, is a form of hope. It says, there is more than this moment. There is more than ourselves. It acknowledges both our fragility and our vast potential, and it affirms that wonder is still the most honest response to existence. So, when you next lie beneath the open sky, Remember, you are a participant in the most complex, most beautiful, most mysterious story ever told. A story still being written, a journey still unfolding. And the stars. They are not just lights in the sky. They are questions, waiting for minds to ask them.
In the distant universe, more than 12 billion light-years away from us, shines a cosmic beacon of almost unimaginable power, an object so radiant that it dwarfs the light of our entire Milky Way galaxy by a factor of hundreds of thousands. This is the quasar J05294351, currently recognized as the brightest and most luminous single object ever discovered in the observable universe. We see it as it was when the cosmos was less than 2 billion years old, a mere teenager in cosmic terms. Despite its immense distance, its light has traveled across the expanding void to reach our telescopes, carrying with it a story of extreme physics, rapid growth, and the violent dawn of galactic structures. This quasar emits light with a luminosity equivalent to more than 500 trillion suns, a torrent of energy so immense that it pushes the very limits of our physical understanding. At the heart of this dazzling celestial powerhouse resides a supermassive black hole, a gravitational monster that is growing at an extraordinary and terrifying rate. Astronomers estimate that this black hole is consuming matter equivalent to the mass of our sun every single day. This ferocious accretion rate is what fuels the quasar's incredible brilliance. The black hole's mass is already estimated to be in the range of tens of billions of times that of our sun. Yet it continues to feed furiously, converting the matter that falls into it into a flood of radiation with record-breaking efficiency. The source of this immense power is a vast and turbulent accretion disk surrounding the black hole. This is a swirling vortex of gas, dust, and shredded stars, likely spanning several light-years in diameter, heated to millions of degrees as it spirals inward. The intense friction and magnetic turbulence within this disk, which is rotating at relativistic speeds, transform the gravitational potential energy of the infalling matter into an astonishing outpouring of high-energy light, a flood of radiation that jets out from the quasar's core in all directions, making it visible across a vast swath of the observable universe. What makes J05294351 especially fascinating for astrophysicists is how its extreme brightness challenges our classical assumptions about the physics of black hole accretion. There is a theoretical maximum luminosity that an object like a quasar can achieve, known as the Eddington limit. This limit represents the point at which the outward pressure of the radiation produced by the accretion disk exactly balances the inward pull of the black hole's gravity on the surrounding gas. If an object were to shine brighter than this limit, the intense radiation pressure should blow away its own fuel supply, effectively shutting down the accretion process. Somehow, this quasar seems to be circumventing these restrictions, shining at a luminosity that appears to be super Eddington. This paradox raises profound new questions about the physics of extreme gravity environments, about the geometry of accretion disks, about the role of magnetic fields, and even about the possibility of subtle changes in physical laws under such extreme conditions. The unprecedented luminosity of J05294351 makes it an invaluable laboratory for testing and refining our astrophysical theories about the growth of supermassive black holes in the early universe and the fundamental physics of matter-energy conversion near an event horizon. It represents a cosmic scenario that pushes our standard accretion models to their theoretical breaking point, forcing astronomers to either refine their classical assumptions or to consider entirely new and more exotic physical mechanisms. The apparent super Eddington luminosity of this quasar implies the existence of unusual physical conditions. One possibility is that the radiation is being emitted anisotropically, meaning it is not shining equally in all directions. If the quasar is producing powerful, beamed jets of radiation that happen to be pointed towards us, it could appear much brighter than it actually is. Another, and perhaps more likely, possibility is that the accretion process itself is different from our standard models. The accretion disk might be geometrically thick and clumpy, rather than thin and uniform, or it might be supported by incredibly strong magnetic fields and turbulent viscosity that allow matter to flow inward at a much higher rate than predicted by classical theory. Detailed spectroscopic studies of the light from J05294351 have revealed prominent broad emission lines, which are the characteristic signature of clouds of extraordinarily hot ionized gas orbiting the central black hole at incredible speeds, approaching several thousand kilometers per second. The analysis of these emission lines provides us with critical clues about the chemical composition of the gas in the early universe. The surprising presence of a high abundance of heavy elements, or metals, such as iron, magnesium, and silicon, in this ancient gas implies that the processes of stellar nucleosynthesis, the creation of heavy elements inside stars, must have occurred remarkably quickly after the Big Bang, much earlier and more efficiently than many traditional models of galaxy formation would suggest. This quasar is telling us that the first generations of stars in its host galaxy must have lived fast and died young, seeding their environment with the building blocks of future stars and planets. Furthermore, the intense and relentless flood of ultraviolet and X-ray radiation emanating from J0529-4351 has a profound and violent impact on its surrounding galactic environment. This phenomenon, known as quasar feedback, occurs when powerful radiative winds and kinetic jets, driven by the black hole's accretion disk, blast through the host galaxy, expelling vast quantities of gas at tremendous speeds. This process can effectively shut down or severely disrupt the process of star formation in the galaxy, and can even influence the evolution of the galaxy on the largest scales. This quasar is not just a passive beacon, it is an active and powerful engine of galactic transformation. Astronomers also use incredibly bright and distant quasars like J05294351 as cosmological lighthouses, powerful tools for probing the otherwise invisible structures that lie in the vast expanses of intergalactic space between us and them. The extremely bright light emitted by this object has been traversing the universe for over 12 billion years. On its long journey to us, it has passed through countless clouds of primordial gas, the vast, wispy filaments of the cosmic web, and the massive, invisible halos of dark matter that surround distant galaxies. Each of these intervening structures absorbs a tiny fraction of the quasar's light at specific characteristic wavelengths. As a result, the spectrum of the quasar's light that reaches our telescopes is imprinted with a forest of absorption lines, known as the Lyman alpha forest. This forest is a cosmic chronicle, a detailed record of the distribution and properties of baryonic matter and the process of cosmic reionization at different epochs in the universe's history. Additionally, J05294351 and other luminous quasars help astronomers to measure cosmological distances and to refine the fundamental parameters of our cosmological model, such as the Hubble constant, which describes the current expansion rate of the universe and the density of dark energy. By studying the intrinsic flickering variability of the quasar's brightness, astronomers can use a technique called reverberation mapping to make precise timing measurements, which can yield independent constraints on these fundamental cosmological constants, helping to resolve some of the current tensions in our understanding of the universe's expansion. Further investigation of this extraordinary object using the next generation of powerful telescopes, including the James Webb Space Telescope, the ground-based Extremely Large Telescope, and future space-based X-ray observatories, will likely provide even more precise and revealing data. These new facilities promise to give us our first deep insights into the quasar's host galaxy, which is currently completely outshone and obscured by the intense glare of the central engine, as well as detailed maps of the immediate environment surrounding the supermassive black hole, revealing the dynamics of the gas flows that are feeding this cosmic monster. Through the subtle effects of gravitational lensing, astronomers might also be able to use the exceptional brightness of J00529435 to uncover previously undetectable structures that lie along our line of sight, including small-scale clumps of dark matter or hidden dwarf galaxies. Such lensing phenomena, magnified and illuminated by the quasar's light, could help astronomers to resolve some of the current tensions in our theories of galaxy formation and our models of the distribution of dark matter. J05229435 thus serves as more than just an extraordinary cosmic beacon. It is also a unique astrophysical laboratory, a place where we can test the predictions of Einstein's general theory of relativity in the ultra-strong gravitational fields that exist near a supermassive black hole. For example, detailed studies of the shape of the iron K-alpha emission lines, which are produced in the innermost regions of the accretion disk, can reveal the effects of frame dragging, a phenomenon predicted by general relativity, where the rotating mass of the black hole literally twists the fabric of space-time around with it. As our observations become increasingly precise, J05294351 could ultimately enable us to test even more speculative physical theories, including various models of quantum gravity or alternative theories that attempt to resolve the paradoxes of black hole singularities and the loss of information. Such research could eventually help us to bridge the long-standing gap between classical astrophysics, general relativity, and the strange world of quantum mechanics. The ongoing studies of this extraordinarily luminous quasar have profound implications that extend even to our most fundamental cosmological enigmas, including the theory of cosmic inflation and the process of early structure formation. The sheer, overwhelming intensity of its radiation not only reveals the physical processes that occur in the most extreme gravitational and energetic regimes in the universe, but it also allows for incredibly high-resolution spectroscopy and polarimetry. These techniques provide us with a unique and unprecedented view into the geometry, the dynamics, and the magnetic environment of the region immediately surrounding this supermassive black hole, a region that is ordinarily far too small and too distant to be resolved. An intriguing and important aspect of such hyperluminous quasars is the potential role they played in the process of cosmic reionization. This was a crucial epoch in the early history of the universe, from about 400 million to 1 billion years after the Big Bang, when the neutral hydrogen gas that filled the cosmos became ionized by the first sources of intense ultraviolet radiation. The immense and powerful flood of ultraviolet and X-ray photons from a celestial beacon like J05294351 indicates that similar, though perhaps less extreme, super-bright quasars, while individually rare, may have collectively contributed significantly to this reionization process, helping to accelerate the transition of the universe from a neutral, opaque state to the transparent and ionized cosmos that we observe today. Furthermore, the exceptional brightness of this quasar allows astronomers to probe and measure very subtle relativistic phenomena, effects that are predicted by theory but are incredibly difficult to observe elsewhere. One such example is gravitational redshift, a phenomenon where photons that are emitted from deep within the quasar's powerful gravitational well lose a small amount of their energy as they climb out and escape into space. This loss of energy manifests as a slight shift in their wavelength toward the red end of the spectrum. Precise measurements of this redshift, by comparing the observed wavelengths of emission lines with their known rest frame wavelengths, could lead to direct and powerful tests of the predictions of general relativity in the ultra-strong gravitational field regime, a place where the theory has never been so rigorously tested. The study of the quasar's spectral variability over time also yields critical astrophysical insights. Variations in its luminosity and in the shape and intensity of its spectral lines can reflect the presence of waves of instability or large-scale turbulence propagating through the accretion disk. These fluctuations may be linked to a key theoretical mechanism known as the magnetorotational instability, or MRI, which is thought to be the primary process that governs the transport of angular momentum in accretion disks, allowing matter to overcome its orbital inertia and fall into the black hole. By examining how these fluctuations propagate through the disk over periods of months and years, astronomers can gain a deeper and more detailed insight into the complex physics that underlies the structure of accretion disks and their long-term stability. From a more practical observational standpoint, the sheer, overwhelming brightness of such luminous quasars makes them ideal calibration points for our new and most advanced telescope systems. They can be used to help refine and calibrate our observational methods across the entire electromagnetic spectrum, from the far infrared to the highest energy gamma rays. Their incredible clarity and relative consistency facilitate the characterization of our instruments and the calibration of our wavelength measurements, thereby broadly contributing to significant improvements in all of observational astrophysics. They are, in a sense, the ultimate cosmic standard lamps. Moreover, these hyperluminous objects might even indirectly support the detection of gravitational waves from the mergers of distant supermassive black hole binaries. The intense radiation emitted by these quasars could ionize or stimulate the gas in the vast regions of intergalactic space, forming environments that might amplify the subtle signals of passing gravitational waves or produce detectable electromagnetic counterparts to these otherwise invisible events. The quasar's powerful and complex magnetic environment also invites extensive and detailed investigation. The high-energy jets and powerful outflows that emanate from its accretion disk suggest the presence of extraordinarily strong and well-organized magnetic fields, which are formed by the complex dynamics of the relativistic plasma swirling around the black hole. By studying the polarization properties of the light emitted by the quasar, astronomers can map the structure and orientation of these magnetic fields, providing invaluable clues about the mechanisms of magnetic field generation and the crucial role that these magnetically driven winds play in the extraction of energy from the accretion disk near the black hole's event horizon. Chemically, the detailed spectral analysis of hyperluminous quasars frequently reveals a surprisingly high abundance of heavy elements, such as iron, magnesium, and silicon. This indicates a rapid and efficient process of stellar nucleosynthesis in the quasar's host galaxy. The presence of such a high degree of metal enrichment, occurring within the first few billion years of the universe's existence, forces astronomers to reconsider the timescales and the processes that were involved in the formation of the first stars, the first supernova events, and the overall chemical evolution of the interstellar medium in the early cosmos. Finally, these ultra-bright quasars serve as invaluable cosmic distance markers, helping us to refine our understanding of the expansion of the universe and the mysterious nature of the cosmological constant, or dark energy. By tracking the correlated fluctuations in the quasar's luminosity across different wavelengths, astronomers can establish a new and more precise type of standard candle, which can help to resolve the current discrepancies between the measurements of the universe's expansion rate that are derived from the cosmic microwave background and those that are obtained from more local distance indicators. Thus, beyond their intrinsic and profound fascination, quasars of such unparalleled and astonishing brightness are fundamentally shaping our understanding of physics, cosmology, and the evolution of galaxies, offering astronomers an extraordinary and irreplaceable window into the most energetic, the most dynamic, and the most enigmatic processes in the entire universe. The discovery and detailed observation of this extraordinary quasar also contribute significantly to our models of how supermassive black holes form in the first place. The extreme conditions that are required for such a massive object to grow so quickly within the limited time frame of the early universe force astronomers to explore unconventional and more exotic mechanisms, such as the direct collapse of massive primordial gas clouds, the rapid mergers of a chain of primordial black holes, or even scenarios involving the gravitational influence of dark matter halos, seeding a process of rapid and efficient black hole accretion. Furthermore, advanced computer simulations of the accretion disks around such luminous quasars indicate that complex relativistic effects, such as photon trapping, may become dominant in these extreme regimes. In this phenomenon, the radiation that is produced deep within the accretion disk, close to the black hole, struggles to escape the immense gravitational pull. This trapping of photons could help to explain how these objects are able to surpass the classical Eddington limit by reducing the outward push of the radiation pressure and allowing matter to continue flowing inward at these unprecedented and ferocious rates. Moreover, the quasar's existence in the early universe, close to the cosmic dark ages, an era when the first galaxies and quasars were just beginning to emerge, makes it a crucial laboratory for understanding the conditions that existed shortly after the Big Bang. Its intense emissions serve as a powerful backlight, illuminating the otherwise invisible clouds of intergalactic gas and enabling astronomers to reconstruct how the very earliest galaxies assembled themselves from the primordial hydrogen and helium gas clouds into the structured, star-forming systems that would eventually populate the cosmos. In addition, the observations of these incredibly bright objects are enhancing our theoretical models of how cosmic dust is formed and how it survives. Despite the incredibly intense and harsh radiation environment that should, in theory, evaporate and destroy dust grains very quickly, these hyperluminous quasars surprisingly host significant reservoirs of dust. Investigating how this dust is able to survive and even thrive in such close proximity to these extremely luminous accretion disks is challenging our current theories of dust grain chemistry, of radiation shielding, and of the processes of grain growth in turbulent and highly irradiated regions of space. Spectropolarimetric studies, which measure the polarization of the light from these objects, have also begun to unravel the complex geometry of these energetic systems. These measurements of polarized light allow astronomers to map the orientation of the accretion disks, the powerful jets, and the obscuring structures often referred to as dusty tori that are thought to surround supermassive black holes. Such detailed polarization maps can enhance our understanding of the intrinsic anisotropy in the radiation fields of these objects, which could be another key to explaining why some quasars are able to achieve such extreme brightness, seemingly in defiance of the theoretical luminosity limits. From an astronomical instrumentation perspective, the study of extremely luminous quasars is stimulating the development of new and innovative methods in fields like adaptive optics, which corrects for the blurring effects of Earth's atmosphere, interferometry, which combines the light from multiple telescopes to achieve higher resolution, and space-based telescopy, the ongoing efforts to resolve the fine structures surrounding these supermassive black holes, including measuring the sizes of their accretion disks or resolving their powerful jets with extremely high resolution, are fostering crucial technological advancements that will be essential for future missions, like the Laser Interferometer Space Antenna or the next generation of very long baseline interferometry networks. The cosmological implications of observing these distant and luminous quasars also extend to the burgeoning field of neutrino astronomy. The hyper-energetic accretion events that power these quasars are believed to produce significant fluxes of high-energy neutrinos through violent particle collisions that occur near the black hole's event horizon. Detecting the neutrinos that are associated with these distant quasars would open a completely new observational window into the fundamental astrophysical processes at play, allowing us to verify our theoretical models of particle acceleration and radiation physics at the most extreme energies. Gravitational lensing by these incredibly bright quasars also provides astrophysicists with a powerful means to probe the intervening structures of dark matter, which are completely invisible through traditional electromagnetic observations. The subtle microlensing of the quasar's light by smaller unseen objects that pass in front of it, such as isolated black holes or dense clusters of stars, becomes detectable thanks to the quasar's immense brightness. This can help to inform our models of the distribution of dark matter on subgalactic scales. Finally, the powerful radio and gamma-ray emissions that often accompany these ultra-bright quasars help us to refine our theoretical models of how relativistic jets are produced. Understanding the complex processes that are able to efficiently channel the immense energy from the accretion disk into tightly collimated relativistic jets involves a deep understanding of complex magneto-hydrodynamics and particle acceleration physics. The observational constraints that are derived from these quasars thus contribute to a broader and deeper knowledge of relativistic astrophysics, a field that is applicable to a wide range of diverse and enigmatic cosmic phenomena, from gamma-ray bursts to the active galactic nuclei that power the jets we see in many nearby galaxies. In summary, these exceptionally luminous and distant objects stand as invaluable and irreplaceable astrophysical laboratories. They challenge our existing theories. They inspire innovative new observational methodologies, and they dramatically enhance our understanding of fundamental physics, of cosmic evolution, and of the nature of the very early universe. Delving deeper into the realm of astrophysical theory, the existence of hyperluminous quasars like J05294351 compels researchers to re-evaluate some of the fundamental assumptions about the early universe, including the initial mass function, which describes the distribution of stellar masses at birth, and the overall rates of star formation in the primordial cosmos. The incredibly rapid accumulation of mass required to form these supermassive black holes so early in the universe's history necessitates either an unprecedentedly dense and gas-rich environment or significantly higher densities of massive stars, potentially indicating subtle shifts in the physics of the early universe or previously unknown and highly efficient mechanisms of star and black hole formation. Furthermore, the detailed physics of accretion disks under these extreme gravitational and radiative conditions remains a vibrant and active area of ongoing theoretical exploration. Current computer simulations indicate that the accretion disk around an ultra-bright quasar might transition into a state known as an advection-dominated accretion flow, or ADAF. In this state, a significant portion of the gravitational energy released by the inflowing matter is not radiated away as light, but is instead directly absorbed, or advected, by the black hole itself. Investigating the properties of ADFs in such extreme contexts could uncover novel and important accretion dynamics and energy dissipation mechanisms, helping to close the theoretical gaps that exist between our classical, simpler accretion models and the more complex and realistic behaviors of relativistic disks. The study of the powerful quasar-induced winds also provides critical insight into the process of kinetic feedback, which is an essential ingredient in our modern cosmological simulations that dictates how galaxies evolve over time. In these hyper-energetic environments, the kinetic outflows, the vast streams of gas that are driven out of the galaxy by the intense radiation pressure from the quasar, can transport heavy elements, or metals, and other enriched materials far out into the intergalactic medium. Understanding this process of galactic enrichment allows cosmologists to refine their numerical simulations that predict the distribution and evolution of metals on the largest cosmic scales, helping to illuminate the cosmic pathways through which the elements that are essential for life are dispersed across vast and empty cosmic distances. Moreover, these luminous quasars indirectly facilitate the study of large-scale cosmological structure, as the bright light emitted by these quasars travels across immense cosmological distances. The subtle distortions that are caused by the gravitational fields of the intervening galaxy clusters provide us with precise and powerful tests of Einstein's theory of general relativity on the largest possible scales. Such measurements can help to identify any potential discrepancies with the theory, or to confirm the predictions of alternative gravitational theories, offering astronomers critical empirical evidence that goes far beyond the local environments of our own solar system or galaxy. Additionally, quasars of such extraordinary and stable brightness can serve as ideal reference sources in the field of precision astrometry, which is the precise measurement of the positions and motions of cosmic objects. By tracking the minute positional shifts of these quasars over decades, astronomers can seek to detect very subtle relativistic phenomena, such as the effects of a background of low-frequency gravitational waves, the orbital motion of binary supermassive black holes, or the micro-lensing effects caused by unseen objects at extreme cosmological distances. These precise positional observations could lead to major breakthroughs in our understanding of the cosmic gravitational wave background and the evolution of the supermassive black hole binaries that are thought to be at the heart of many galaxies. The powerful ultraviolet and X-ray emissions from these quasars also have a profound influence on the chemistry of the intergalactic medium. The high-energy photons emitted by the quasar ionize the surrounding gas, fundamentally altering its chemical composition and its thermal structure. Detailed observations of the absorption lines from this gas allow astrophysicists to map the distribution of highly ionized elements like carbon, oxygen, and neon, thus shedding light on the temperature and density distribution of the diffuse cosmic gas that fills the space between galaxies. These are vital components in our cosmic simulations of structure formation and evolution. From a broader theoretical standpoint, the observed abundance of extremely bright quasars at high redshift poses some significant challenges for our standard models of cosmic inflation and the timelines of structure formation. Our standard cosmological simulations must either account for much earlier formation times for these large-scale structures or reconsider some of the fundamental assumptions about the nature of the initial density fluctuations that were present shortly after the Big Bang. Such insights could ultimately reshape the entire theoretical framework of our cosmological history. Furthermore, the detailed observations of these hyper-energetic quasars serve as invaluable laboratories for the study of plasma physics under extreme conditions, including processes like magnetic reconnection, which is a key mechanism in the acceleration of particles and the launching of powerful jets around compact objects. A detailed analysis of the patterns of emission variability and the polarization signatures of the light from these objects can provide crucial clues about how these complex magnetic processes unfold in the most extreme astrophysical environments. advancing our understanding of high-energy astrophysics and plasma dynamics in general. Finally, these luminous cosmic beacons offer us incredible opportunities for multidisciplinary studies that can involve nuclear physics, particle physics, and quantum field theory. The observations of intense gamma-ray flares, the potential detection of associated neutrino emissions, and the study of the relativistic particle jets allow physicists to study the processes of particle acceleration, the effects of quantum electrodynamics in strong electromagnetic fields, and possibly even to probe for the existence of new physics, such as the signatures of actions or dark photons, which are hypothetical particles proposed by theories that go beyond the standard model of particle physics. Thus, beyond their intrinsic astronomical interest, these extraordinarily luminous quasars hold an immense potential for revolutionizing numerous branches of physics, fostering deeper and more profound insights into the most fundamental cosmological phenomena, the world of particle physics and the very earliest phases of our universe. The study of these exceptionally luminous quasars is also advancing our understanding of the complex instabilities that can arise in accretion disks that are dominated by radiation pressure. In such intense and extreme environments, the outward push of the radiation can exceed the inward pull of gas pressure by many orders of magnitude. This can trigger a range of powerful instabilities, such as thermal viscous instabilities or the so-called photon bubble instability. These phenomena can cause the accretion disk to fragment into dense, optically thick clumps, or can induce rapid and dramatic fluctuations in the quasar's luminosity and the overall structure of the disk, effects that are directly observable through precise and long-term photometric monitoring. Furthermore, a detailed analysis of the multi-wavelength emission patterns of these luminous quasars, from the lowest energy radio waves to the highest energy gamma rays, allows astronomers to build complex models of the interplay between different radiation mechanisms, such as synchrotron radiation, which is generated by relativistic electrons spiraling in powerful magnetic fields, and inverse Compton scattering, a process where low-energy photons gain a huge amount of energy through collisions with high-energy electrons. Studying how these different processes balance each other out in these extreme environments provides us with deeper insights into the mechanisms of particle acceleration and cooling under the most extreme astrophysical conditions. Hyperluminous quasars also provide us with critical observational constraints on the opacity of the intergalactic medium at very high redshifts. As the photons from these distant quasars traverse the vast cosmological distances to reach us, their interactions with the neutral hydrogen and helium that filled the early universe produce distinctive and powerful absorption features in their spectra, particularly the Gunn-Peterson trough, which are invaluable for dating the epoch of Ryanization with a high degree of precision. Thus, these quasars are crucial cosmic chronometers that help us to calibrate our cosmological models concerning the universe's historic transition from a neutral and opaque state to the ionized and transparent cosmos that we inhabit today. Additionally, the fact that these quasars, which are emitting such exceptional luminosities, are able to exist at all challenges our theoretical models of how cosmic dust survives in the universe. Standard theories would suggest that dust grains should be very rapidly destroyed by the intense and energetic photon fields that are produced by these objects. And yet, observations have shown that significant reservoirs of dust remain present in these extreme environments. Resolving this apparent paradox involves re-evaluating our understanding of the processes of dust grain growth, destruction, and radiation shielding, which could potentially lead to a major revision of our understanding of grain physics and the processes of chemical enrichment in the turbulent and highly irradiated regions of the early cosmos. Another intriguing area of research that is influenced by these powerful quasars is the study of starburst-quasar interactions. Astronomers have long hypothesized that there is a complex feedback loop in which periods of rapid star formation, or starbursts, in the host galaxy provide the fuel for the central quasar, and the quasar, in turn, subsequently suppresses or regulates further star formation through its intense radiation-driven outflows of gas. By making detailed observations of the gas motions, the star formation rates, and the distribution of molecular gas in the regions immediately surrounding these hyper-energetic galactic nuclei, astronomers are able to refine their feedback models, helping to clarify the complex and co-evolutionary relationship that exists between galaxies and their central supermassive black holes. The extreme brightness of these distant quasars also enables astronomers to probe previously inaccessible cosmic epochs, most notably the epoch of first galaxies, the period when the very earliest galactic structures were just beginning to assemble. By using the light of these quasars as a powerful backlight, we can illuminate these early, faint galactic structures, providing us with insights into the nature of the primordial stellar populations, the so-called Population 3 stars, the formation of the first galactic clusters, and the growth of dark matter halos at unprecedentedly early cosmic times. On the experimental frontier, the next generation of gravitational wave observatories, such as the Laser Interferometer Space Antenna, or LISA, aim to detect the low-frequency gravitational waves that are generated by the mergers of supermassive black holes, a process that is likely to involve these luminous quasars. By correlating the detection of these gravitational wave events with the electromagnetic signals from the quasars, we could confirm our models of how black holes grow, the dynamics of their accretion, and the scenarios of merger-driven galaxy evolution, a discovery that would profoundly influence the future of gravitational wave astronomy. Moreover, the study of these hyperluminous quasars is providing us with deep insight into the evolution of cosmic magnetic fields. Their strong and often polarized emissions indicate the presence of well-organized magnetic fields with extraordinary strengths that have a major influence on the dynamics of accretion, the collimation of jets, and the acceleration of particles. Understanding the origins and the evolution of these powerful magnetic fields is fundamental for building comprehensive models of galaxy formation and the process of magnetogenesis in the infant universe. In addition, the extraordinary radiation fields that are produced by these quasars are helping astrophysicists to test the predictions of quantum electrodynamics, or QED, in the presence of intense gravitational and magnetic fields. Exotic phenomena such as vacuum birefringence, a state where the vacuum itself is predicted to behave as a birefringent medium under extreme magnetic conditions, could become observable, allowing for unprecedented tests of the fundamental principles of physics. Finally, these hyper-energetic quasars indirectly support our cosmological studies of the propagation of cosmic rays and the search for the sources of high-energy neutrinos. The extreme particle acceleration processes and the immense energies that are inherent to these quasars make them ideal natural laboratories for the study of particle acceleration physics. They could potentially help us to identify the distant and mysterious sources of the ultra-high-energy cosmic rays and neutrinos that we detect here on Earth, thus uniting the fields of astrophysics and particle physics in a single, coherent observational framework. In this way, the study of these exceptionally luminous quasars is not only enriching our astrophysical theories, but also promises to answer some of the most profound and fundamental scientific questions about the nature of our universe. Connecting cosmology, fundamental physics, and the astrophysics of the early universe in a single, unified scientific narrative. The exploration of these enigmatic and radiant cosmic beacons is pushing the very limits of human knowledge, prompting us to ask deeper and more profound inquiries into the very nature of reality itself. Their extreme and almost impossible luminosity hints at the presence of unseen processes that may be lurking just beneath the surface of our observable physics, compelling scientists to consider novel and exotic mechanisms. Could these objects, shining brighter than entire clusters of galaxies, be subtle gateways to undiscovered physical laws or to cosmic realms that we have yet to comprehend? Perhaps the physics at play is tied to the mysterious nature of dark matter, dark energy, or even the existence of hidden extra dimensions of reality. Intrinsically, the immense gravitational pull of these quasars might also enable astronomers to one day test some of the more speculative but profound ideas in theoretical physics, such as the holographic principle, a theory which suggests that all of the information about our three-dimensional universe might be encoded on a distant two-dimensional boundary surface, like the event horizon of a black hole. The detailed observations of subtle quantum or gravitational phenomena in these incredibly intense environments could one day unlock the first clues about how space, time, and gravity intertwine at the deepest and most fundamental quantum scales, possibly bringing scientists closer to resolving some of the long-standing and deeply perplexing enigmas that surround the nature of black hole singularities. Furthermore, the extraordinary particle acceleration environments that are found near these luminous giants could shed new light on the enduring mysteries of high-energy cosmic rays, the sources of cosmic neutrinos, and the potential signatures of dark matter annihilation. Could the immediate vicinity of these quasars, a region of space that is bathed in intense radiation and powerful twisted magnetic fields, be a natural particle accelerator that is far more powerful than any human-made collider could ever hope to be? Could the subtle and as yet unexplained signals in their spectra, or in the fluxes of cosmic rays that we observe here on Earth, be hinting at interactions that involve new and undiscovered fundamental particles? Moreover, cosmologists have begun to speculate whether the distribution of these extremely luminous quasars in the early universe holds hidden clues about the process of cosmic inflation, the brief but explosive period of expansion that is thought to have occurred just moments after the Big Bang, a process that shaped the universe as we know it today. The subtle patterns that may be imprinted on the large-scale distribution of these ancient and brilliant quasars might provide us with the first direct observational signatures of the physics of inflation, offering crucial tests for theories that are currently limited to the realm of pure theoretical speculation. Astrobiologists, too, have begun to ponder the indirect and complex implications of these hyperluminous quasars for the possibility of life existing elsewhere in the universe. While their intense and powerful radiation would almost certainly sterilize any nearby planets, could their powerful galactic outflows be responsible for distributing the essential elements for life, such as carbon, oxygen, and phosphorus, across vast cosmic distances, effectively seeding distant galaxies with the necessary building blocks of life billions of years before our own Earth even formed? Are these extraordinarily bright and powerful objects, which are so paradoxically destructive at close range, actually vital and necessary participants in the grand cosmic chemical cycles that are essential for the universal emergence of life? Equally compelling is the potential to use these quasars as a new and more precise type of standard candle cosmic lighthouses, whose predictable luminosity variations across vast cosmological distances could help us to refine our models of precision cosmology beyond their current capabilities. Could these detailed measurements eventually reveal subtle and unexpected deviations from our standard cosmological model, pointing astronomers toward new and unknown forms of dark energy or previously undetected forms of cosmic spatial curvature? From a more speculative viewpoint, the mind-boggling energies that are involved near these quasars ignite the imagination about the possibility of other, as yet unknown, astrophysical phenomena. Could their immense gravitational fields be capable of twisting space-time sufficiently to form transient wormholes or other exotic gravitational lensing patterns? Could these luminous and violent giants be hosting unimaginable and truly alien astrophysical entities, such as exotic compact objects like boson stars? Or could they be interacting with hypothetical cosmic strings that are passing nearby, leaving behind discernible and unique signatures for our most careful observers to find? Ultimately, these hyperluminous quasars symbolize humanity's relentless and unending quest to understand the cosmos at its most extreme and most fundamental levels. As astronomers and physicists continue to refine their instruments and their theoretical techniques, these powerful celestial beacons promise to deliver new discoveries that will not only enhance our astrophysical understanding, but will also have the potential to completely reshape our most fundamental conceptions of reality itself. Each new observation of these distant and brilliant objects thus becomes a thrilling and important step toward decoding the deepest cosmic mysteries that have captivated and inspired thinkers since the dawn of human consciousness. Beyond their immense scientific importance, these extraordinarily luminous and distant quasars also serve as profound and humbling reminders of nature's incredible capacity to surpass the limits of human imagination. They challenge scientists to venture beyond the safety and comfort of their established theoretical frameworks, urging them to explore new, radical, and often counterintuitive hypotheses, such as the effects of quantum gravity on the nature of singularities, alternative formulations of the geometry of space-time, or the existence of unconventional properties of dark matter. Could the spectacular luminosity and the incredibly rapid growth of these supermassive black holes be a sign of their interaction with previously undetectable quantum fields, or with hidden extra dimensions of reality that are currently beyond the reach of our perception? Astrophysicists also speculate on the observational signatures that may arise from the mergers of these quasars, rare and incredibly violent events that are expected to shake the very fabric of space-time itself. Such titanic and cataclysmic encounters, which would involve the collision and the eventual unification of 2 billion solar mass black holes, could emit powerful and detectable gravitational waves that could be observed by the next generation of space-based detectors. Could the detailed electromagnetic observations of these events, when correlated with their gravitational wave signatures, revolutionize our understanding of the nature of gravity, either confirming or refuting the predictions of Einstein's theory in the most extreme environments? Furthermore, theoretical physicists are exploring how these hyperluminous quasars might be able to illuminate deeper insights into the nature of entropy and the flow of information within the cosmos. The intense and complex energy transformations that are occurring near the event horizons of these objects provide us with unprecedented natural laboratories for testing some of the most profound and difficult concepts in modern physics, including the principles of black hole thermodynamics, the ideas of holographic information encoding, and even the subtle interactions that are thought to exist between gravity and the theory of quantum information. Could a detailed and long-term study of these quasars eventually lead to a resolution of the famous black hole information paradox, which remains one of the greatest and most stubborn unsolved mysteries in all of physics? From a cosmological perspective, the brightest of these quasars also serve as powerful probes of the fundamental assumptions of universal homogeneity and isotropy, which are the central pillars that underpin our entire standard model of cosmology. The detection of even slight and subtle irregularities or directional anomalies in the distribution of these quasars across the vast scales of cosmic distance could hint at the existence of large-scale cosmic anisotropies or significant deviations from our standard cosmological assumptions. This could potentially lead to paradigm-shifting revisions of our entire cosmological theory. In addition, the remarkable stability and the enduring visibility of these hyperluminous quasars over billions of years of cosmic time pose some intriguing possibilities for observational astronomy. Their persistent brightness on these immense timescales allows astronomers to compare the properties of their ancient emitted radiation with modern observations, which could potentially allow us to identify subtle cosmic variations over time, such as a drift in the values of the fundamental constants, a change in the nature of the physical laws, or an evolution in the properties of dark energy. Could these quasars be the ultimate cosmic reference points, allowing us to track the evolving nature of the universe itself across immense and otherwise inaccessible stretches of time? Moreover, the complex interplay that exists between these hyperluminous quasars and their host galaxies is opening up tantalizing new possibilities for understanding the processes of galaxy formation and evolution. A deeper understanding of how these incredibly energetic objects are able to impact the star formation rates, the morphology, and the chemical composition of their host galaxies is deepening our knowledge of the co-evolutionary relationship that exists between galaxies and their central supermassive black holes. Could it be that quasars of such astonishing and brilliant power are fundamentally shaping the destinies of their host galaxies, regulating the grand cosmic cycles of birth, destruction, and renewal over the course of eons? Even more provocatively, some physicists have begun to consider whether the most luminous of these quasars could shed some observational light on the existence of exotic cosmological objects like primordial black holes, which are hypothetical remnants of the Big Bang itself. Could the tiny, ancient primordial black holes that may have been captured in orbit around or are being consumed by these colossal supermassive black holes be leaving behind detectable and unique imprints on the quasar's radiation or on its gravitational wave emissions, revealing profound new insights into the physical conditions that existed just fractions of a second after the birth of our universe? Ultimately, these luminous quasars represent a new and exciting cosmic frontier, the exploration of which may forever alter our scientific understanding and our philosophical perspective. Their extraordinary and often paradoxical properties are posing some of the most fundamental questions we can ask. What unknown physical laws are awaiting discovery within their turbulent and fiery hearts? Do entirely new and undiscovered forms of matter or energy operate in these extreme and violent environments? Could the detailed and long-term study of these cosmic giants provide humanity with profound new insights into the nature of our own existence and our true place within the vast and mysterious universe in pursuing these celestial enigmas? Astronomers and physicists are embarking on one of humanity's most thrilling and important intellectual adventures, pushing the boundaries of our knowledge, inspiring technological innovation, and transforming our understanding of the universe from the smallest quantum scales to the grandest cosmic expanse. Exploring the radiant depths of these powerful cosmic beacons might, in time, even help us to unravel the deep and enduring mysteries that surround the nature of cosmic acceleration and the enigmatic properties of dark energy. Their incredible luminosity and their profound clarity at immense cosmological distances offer us an unparalleled and powerful tool for precisely mapping the expansion history of the entire universe. By meticulously charting the subtle variations in their luminosity across the vast scales of the cosmos, astronomers might one day be able to detect the faint and hidden signals or anomalies that could point to the existence of undiscovered components that are influencing the evolution of the cosmos. Could the subtle and complex patterns that are hidden Deep within the ancient radiation of these extraordinary and brilliant quasars hold the key to resolving our era's greatest and most profound cosmological enigmas. From a gravitational perspective, these superluminous quasars also present us with tantalizing and unique opportunities for investigating any potential deviations from Einstein's cherished theory of general relativity. Their incredibly intense gravitational fields and their highly relativistic environments create the ideal and natural testing grounds for measuring the subtle and difficult-to-detect effects that are predicted by various modified theories of gravity, including the so-called scalar tensor theories, or the more exotic higher-dimensional models. Could the precise and detailed observations of the emission lines or the relativistic jets that are produced near their central engines ultimately provide us with the first empirical evidence that could support these revolutionary new theories of gravity and the very nature of space-time? Furthermore, the complex magnetic field structures and the extreme plasma behaviors that are observed in the regions surrounding these luminous giants are opening up new windows into the regimes of plasma physics that are completely unattainable in any of our terrestrial laboratories. The detailed observations of the coherent electromagnetic flares, the violent magnetic reconnection events, and the powerful particle acceleration that occurs near these cosmic dynamos are offering astrophysicists a chance to better understand the fundamental magneto-hydrodynamic processes that govern a wide range of phenomena. From the flares on our own sun to the acceleration of cosmic rays and the nature of pulsar wind nebulae. Could the detailed and long-term studies of these quasars fundamentally enhance our knowledge of the principles of plasma physics, guiding significant advancements across a wide range of multiple scientific disciplines? Equally intriguing is the possibility that these supermassive and hyperluminous quasars could indirectly inform our ongoing searches for extraterrestrial intelligence. While their intense and powerful radiation would certainly render any nearby regions completely hostile to the kind of life that we know, their immense visibility and their recognizable radiation signatures across billions of light-years of space may serve as a kind of universal marker or a cosmic beacon, a signpost that would be recognizable even by distant and technologically advanced civilizations. Could these remarkable and powerful phenomena play a role in any hypothetical strategies for interstellar communication, or could they serve as natural and reliable reference points in any form of extraterrestrial navigation? The very existence of such objects forces us to consider the universe on a scale that is both humbling and inspiring, a universe of immense power, beauty, and mystery.